You're sitting still right now. Or at least, you think you are. You feel motionless, a point of calm in a quiet room. The chair beneath you feels solid. The air is settled. The world, just for a moment, has paused. It's a universal human experience, this feeling of stillness. We look for it in meditation, we find it in quiet moments, and we take it for granted in the objects all around us. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if I told you that this feeling is an illusion? A profound, beautiful, and maybe even necessary illusion, but an illusion nonetheless. As science relentlessly peels back the layers of reality, it's uncovered a mind-bending secret. It turns out that you, and everything around you, are caught in a cosmic dance of such astonishing speed and violence that the very concept of stillness completely unravels. From the grand waltz of galaxies to the frantic shudder of a single atom, there is no escape from motion. Together, we're going to dismantle the idea of stillness piece by piece. We'll travel from the familiar world of our everyday lives to the unimaginable speeds of our journey through the cosmos. Then, we'll shrink ourselves down, past the molecules and atoms, into a realm so strange it defies all intuition, the quantum world, where the laws of reality themselves forbid anything from ever, truly, holding still. By the end, the simple act of sitting in a chair will be transformed. You won't see an object at rest, but a universe in perpetual, glorious motion. You think you can sit perfectly still, but science has a mind-bending secret for you. It turns out every atom in your body is caught in a never-ending cosmic dance that makes true stillness impossible. The quiet you feel? It's a lie. The solidity of the world is just a temporary agreement. And the quest to find a single point of absolute rest in this universe will lead us to the very edge of reality, to a place where existence itself is defined not by being, but by becoming. The illusion of stillness, a matter of perspective. Let's start with a simple, foundational idea. Motion is relative. This concept, which Einstein sharpened to a fine point, is the first crack in the facade of stillness. Imagine you're on a train moving at a perfectly smooth 100 kilometers per hour. You pour a cup of coffee. The liquid falls straight down. You set the cup on the table, and it sits there, perfectly still. From your perspective, your reference frame, you and the coffee are motionless. But your friend, standing on the platform watching you speed past, sees something entirely different. They see you, the train, and your still cup of coffee hurtling by at 100 kilometers per hour. To them, your coffee isn't still at all, it's a projectile. So, who's right? The profound insight of physics is that you both are. There is no absolute, privileged place to stand and judge. Motion only has meaning relative to something else. This simple idea explodes in scale when we look at our place in the universe. You feel like you're sitting still in your room, but that room is on a planet that's spinning on its axis. Depending on your latitude, your still body is moving at over 1,600 kilometers per hour right now. Fastest if you're near the equator. And that's just the beginning. Our entire planet is locked in an orbit around the Sun. To make that trip in just 1 year, Earth has to travel at a staggering speed. Every second, you, your chair, and everything you hold dear are carried about 30 kilometers through space. That's an orbital speed of roughly 107,000 kilometers per hour. You're riding a celestial bullet, and you don't feel a thing. Let's zoom out even further. Our Sun isn't a fixed point. It's just one of hundreds of billions of stars in the Milky Way galaxy. The entire solar system is orbiting the supermassive black hole at the galactic center. This journey is so vast it takes over 200 million years to complete a single lap, at a speed that's almost beyond comprehension. About 828,000 kilometers per hour. Even our galaxy isn't sitting still. The Milky Way is part of a local group of galaxies, all gravitationally tangled and moving in relation to one another. Our galaxy is currently hurtling toward our nearest large neighbor, Andromeda, at a brisk 400,000 kilometers per hour. So, the next time you feel perfectly still, remember, you're spinning on a planet, which is hurtling around a star, which is screaming around a galaxy, which is itself falling through intergalactic space. The stillness you perceive is just a trick of local perspective. Because everything in your immediate environment is moving along with you, you have no local sensation of this incredible velocity. At this point, you might ask, is there any ultimate background we can use to measure our true speed? For a long time, the answer was thought to be no. But we have found something close, the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, a faint radiation that fills all of space. It's the closest thing we have to a rest frame for the universe itself. And when we measure our motion relative to the CMB, we find our entire solar system is moving at about 1.3 million kilometers per hour toward the constellation Leo. So, the first layer of the mystery is peeled back. On the grand, cosmic scale, there is no stillness. But this only addresses the motion of things. What about the motion within them? Can an object be internally still? To answer that, we have to leave the cosmos behind and begin our journey to the very, very small. The classical dream of stillness. Before we dive into the truly bizarre quantum world, let's pause in a more familiar landscape, the physics of Isaac Newton. For centuries, this was our blueprint for reality, a magnificent clockwork universe. And in this clockwork, stillness seemed not only possible, but essential. Newton's first law of motion, the law of inertia, is the bedrock of this classical dream. It says an object at rest will stay at rest unless acted on by an external force. Here, at rest, means having a velocity of exactly zero. In the classical view, if you could take a perfect sphere, place it in a perfect vacuum, and shield it from all forces like gravity or friction, it would be truly still. It would have a definite position and zero velocity, forever. This framework is incredibly useful. It lets us build bridges and send rockets to the moon. But even in this classical picture, the dream of perfect stillness is a fantasy. A perfect vacuum or perfect isolation doesn't exist. Every object is constantly bathed in gravitational fields from every other object in the cosmos. Even the faint light from distant stars exerts a tiny, almost infinitesimal pressure. More fundamentally, the very fabric of spacetime is expanding. The space between galaxies is stretching. So even a perfectly isolated object would still be carried along by the expansion of the universe. The classical dream, then, was of a stillness that could only exist in a hypothetical, sterile universe, where atoms were like tiny billiard balls that could be brought to a complete stop. But as our tools got better in the early 20th century, we peered into the heart of matter. And what we found there wasn't quiet, orderly, or still. We found chaos, uncertainty, and ceaseless energy. The classical dream was about to be shattered by a new and far stranger reality, quantum mechanics. This new physics wouldn't just say stillness is difficult, it would reveal that it's fundamentally impossible. The journey inward, a world in motion. Now our investigation takes a dramatic turn. We're leaving the dance of galaxies behind and zooming into the very heart of the matter you're made of. Let's take a glass of water sitting on a table. To our eyes, it's the picture of calm. But this is a statistical illusion, an average of an unimaginable amount of microscopic chaos. Part A. The atomic dance. If we could magnify our view a billion times, that placid water would become a roiling frenzy. We'd see trillions of hydrogen oxide molecules vibrating, rotating, and colliding with each other billions of times per second. This is thermal motion. The temperature of the water is just a measure of the average energy of this molecular dance. The warmer the water, the more violent the dance. This leads to a logical question. What if we just keep cooling it? As we lower the temperature, the molecules slow down. They eventually lock into a crystal structure, ice. But even in the ice, the atoms aren't still. They're trapped, but they continue to vibrate furiously in their fixed positions. So let's keep going. Imagine we have a perfect refrigerator, capable of pulling out every last bit of thermal energy. We cool our sample down, toward the absolute limit of cold, absolute zero. That's 0 Kelvin, or minus 273.15 degrees Celsius. Classically, this is where all motion should stop. The atoms should finally come to a complete and total rest. We should have finally achieved perfect stillness. But have we? Is it truly possible to freeze an atom in its tracks? The answer, thanks to the strange laws of quantum mechanics, is a resounding and definitive no. Part B. The quantum revelation, the end of stillness. In the early 20th century, a revolution in physics revealed that the classical rules of Newton just don't apply to the world of atoms and electrons. This new rulebook, quantum mechanics, describes a reality that is probabilistic, fuzzy, and fundamentally uncertain. At its heart is one of the most famous ideas in all of science, the Heisenberg uncertainty principle. The uncertainty principle states there's a fundamental limit to how precisely you can know certain pairs of properties of a particle at the same time. The most famous pair is position and momentum. The principle says the more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. It's like this. If you use a very fast shutter speed to photograph a speeding car, you get a sharp image of its position. But from that single frozen instant, you have no idea how fast it was going. If you use a long exposure, you get a blurry streak. Now you have a good sense of its motion, but its exact position at any given moment is completely uncertain. The uncertainty principle says this trade-off isn't a flaw in our tools, but an inescapable property of nature itself. Now, let's apply this to our quest for stillness. For a particle to be perfectly still, we would need to know two things with perfect certainty: its exact position and its momentum, which would be exactly zero. But the uncertainty principle forbids this. It's a mathematical impossibility. If you knew the momentum of a particle was exactly zero, the uncertainty in its position would become infinite. In other words, a perfectly still particle could be anywhere in the entire universe. Conversely, if you pinned down a particle to a single point, its momentum would become infinitely uncertain. It would be in a state of infinitely violent, unpredictable motion. This is the quantum nail in the coffin of stillness. It isn't just difficult to bring a particle to a stop, it's forbidden by the fundamental laws of reality. Part C. Zero-point energy. This mandatory, inescapable quantum jiggle has a name: zero-point energy. It is the lowest possible energy that a quantum system can have. Even if you cool a substance to absolute zero, its atoms will still vibrate. This isn't leftover heat, it's a fundamental energy of being, woven into the fabric of reality by the uncertainty principle. Think of a guitar string. You can pluck it to make a loud note, a high energy state. As the sound fades, the vibrations get smaller, a lower energy state. You might think it could eventually become perfectly flat and motionless, but in the quantum world, this isn't allowed. The string must always retain a tiny, residual quiver. This minimum quiver is its zero-point energy. This isn't just theory. We see its effects in the real world. Under normal pressure, liquid helium is the only element that will not freeze solid, no matter how cold you make it. Even as you approach absolute zero, the zero-point energy of its atoms is so great that they vibrate with enough energy to prevent them from locking into a solid crystal. It remains a liquid, a quantum fluid, a permanent testament to the impossibility of stillness. Our journey inward has led to a profound revelation. Stillness is a lie, not just because of our cosmic speed, but because at the most fundamental level, The building blocks of our world are forbidden from ever being still. But what about the space between the atoms? What about a perfect vacuum? Is it possible that the void itself is truly still? The fabric of reality is not quiet. We've discovered that matter can't be still. Its particles are forever locked in a quantum dance. But surely, the vacuum of space, the emptiness between the particles, must be the home of true stillness. We've always imagined the vacuum as the ultimate nothingness. No matter, no energy, no motion. This, too, turns out to be a comforting illusion. Modern physics has revealed that the vacuum of space is not empty at all. It is a seething, bubbling, unimaginably energetic place. Part A. The buzzing void, quantum field theory. Our modern understanding of reality is called quantum field theory, or QFT. It tells us that the most fundamental things in the universe aren't tiny particles, but vast, invisible fields that permeate all of spacetime. There's an electron field, a photon field for light, and so on. Every particle is just a local vibration, a ripple, in its corresponding field. Just like quantum particles, these fields are subject to the Heisenberg uncertainty principle. This means a field can never be perfectly off. Even in its lowest energy state, what we call the vacuum, a field must retain a minimum amount of energy and must constantly fluctuate. This leads to the wild concept of quantum foam. Because the fields in the vacuum are always fluctuating, they can borrow enough energy from nothingness to create pairs of virtual particles. For an infinitesimally brief moment, a particle and its antiparticle can pop into existence, then annihilate each other, returning their borrowed energy. This is happening everywhere, all the time. The vacuum of empty space is a churning foam of potential, with virtual particles popping in and out of existence faster than we can imagine. The nothing of the void is actually a hotbed of activity. Part B. The inner life of matter. Now that we know the void is restless, let's zoom back into a particle, like a proton in the nucleus of an atom. Is there any stillness inside? The answer is a chaotic no. A proton isn't a single fundamental ball. It's made of three smaller particles called quarks, bound together by gluons. The inside of a proton isn't three quarks sitting peacefully. It's a maelstrom. The quarks are moving at near the speed of light, constantly exchanging a dizzying swarm of virtual gluons. And what about the electron orbiting the nucleus? It isn't a tiny ball. It exists as a probability cloud, a region of space where the electron is likely to be found. It doesn't move from point A to point B. It exists as a wave of possibility that fills a volume of space. Part C. The philosophical implications. This brings us to a deep shift in our understanding of existence. Classical physics gave us a world of things. A rock is a thing with a location and a static identity. But quantum physics gives us a world of processes. An electron isn't a static thing. Its very existence is an event, a continuous fluctuation of a field. If every particle is a process, and the vacuum between them is a process, then the entire universe is a process. It is not a static object, it is a dynamic, evolving symphony. Stillness requires a static thing to be still. But quantum mechanics tells us that at the most fundamental level, there are no static things. There is only the dance. We've journeyed from the edge of the cosmos to the heart of the quantum foam. And everywhere we've looked, we have found only motion. So where does this leave us? Is the stillness we feel in a quiet moment a complete lie? Finding stillness in a world of motion. So, we've established that from a physical standpoint, absolute stillness is impossible. Your body is a cascade of motion, from its cosmic velocity to the ceaseless quantum jiggle of its every atom. What do we do with this knowledge? Does it mean the calm we feel when we sit by a lake is a delusion? No, it enriches it. It makes it more precious. The stillness we experience is a stillness of scale and reference. When you sit in your chair, you're still relative to the chair and the room around you. The frantic dance of your individual atoms averages out on the macroscopic scale of your body. The trillions of random vibrations cancel each other out, resulting in a state of large-scale composure. That is a real, measurable, and meaningful kind of stillness. It's relative stillness, and it's the only kind that has ever mattered for our survival. Physics doesn't steal our experience of stillness, it redefines it. It tells us that the calm we seek is not a stop in motion, but a * harmony of motion. It's the difference between a chaotic mess of instruments all playing different tunes, and a symphony where all those individual movements combine to create one coherent, beautiful piece of music. Your body, sitting still, is a symphony. This also invites us to distinguish between physical stillness and psychological stillness. The peace we find in meditation isn't a function of our atoms slowing down. It's a quieting of the noise in our minds. It's about bringing our own consciousness into a state of relative rest. Just as we can choose a reference frame where we're still, we can choose to cultivate a mental frame of reference that is calm and centered, even as the world around us and within us continues its relentless dance. We started with a simple feeling, being still. Through the lens of physics, we've seen how this feeling conceals a universe of astonishing motion. We've traveled millions of kilometers per hour with our planet, star, and galaxy. We've plunged into the heart of matter to find a place where even at absolute zero, a fundamental quantum jiggle persists. We've even stared into the void and found not emptiness, but an energetic sea of virtual particles. The truth is inescapable. There is no absolute rest. Motion is fundamental. Change is the one true constant. The world you see is not a collection of static objects, but a series of dynamic events. You are not a fixed entity, but a temporary, intricate pattern in the endless flow of cosmic energy, a symphony of trillions of atomic vibrations. The stillness you feel is not a lack of motion, but a moment of equilibrium. It is a precious, fleeting island of perceived calm in an infinite ocean of change. It is a gift of perspective. And now, knowing this, perhaps that feeling of stillness can be appreciated even more. It's a reminder that in a universe defined by its relentless, beautiful, and eternal dance, we can still find moments of peace. Not by stopping the dance, but by learning to move with it. If this journey into the heart of reality has given you a new perspective, consider subscribing for more explorations into the physics of our universe. And let us know in the comments, what does stillness mean to you now? The physics of stillness explains slowly. Take a look at your hand, or the table in front of you, or the device you're watching this on. For our entire lives, our senses have told us a simple, consistent story. Some things move, and some things are still. A rock can sit on the ground, motionless, for 1,000 years. It is a picture of perfect, absolute rest. A kind of certainty in a world of change. That certainty is an illusion. It is not a small illusion. It is perhaps one of the most profound and universal stories our senses tell us. The truth is that the concept of stillness, as we understand it, does not exist anywhere in the universe. Not in the heart of a diamond, not in the coldest voids of space. What you perceive as a solid, static object is, in reality, a scene of almost unimaginable activity. A universe in constant, frantic motion. An unending dance of particles that began with the birth of the cosmos and will continue until its very end. In the next few minutes, we're going to peel back the layers of that illusion. We will journey from the world we can see and touch, down into a realm so small it defies intuition. We will discover what's really happening inside that still object, and in doing so, we will uncover a fundamental truth about the nature of everything. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a quiet room, or somewhere in between, feel free to share where you're watching or listening from. The first clue, a botanist's accidental discovery. Our journey into the hidden motion of the universe begins not with a particle accelerator, but in the year 1827, with a Scottish botanist named Robert Brown. Brown was a man of meticulous observation. One afternoon, he was examining pollen grains suspended in a drop of water, hoping to learn more about plant fertilization. But what he saw under his microscope had little to do with botany. It would become the first quiet glimpse into a different kind of reality. He noticed that tiny particles within the pollen grains were moving. They weren't sinking or flowing with a current. They were jittering and zigzagging in a completely random way. A strange, rapid oscillatory motion that seemed to have no cause. His first thought, as a botanist, was that he was witnessing the very essence of life, some vital force. But Robert Brown was a good scientist. He repeated the experiment, this time with pollen from plants that had been preserved for over a century. The motion was still there. He then ground up tiny fragments of rock and dust, and even a chip from a sphinx, and suspended them in water. To his astonishment, they danced in exactly the same way. This was not a life force. This was something else, something fundamental. The phenomenon, this ceaseless, random jiggling, was named Brownian motion in his honor. Brown himself could not explain what was causing it. He didn't know it at the time, but he had stumbled upon the first direct, visible evidence that the world was not as it seemed. He was seeing the result of a hidden world of motion, a world where billions of unseen particles were colliding with the pollen grain, pushing it around. It would take nearly 80 years for the explanation to arrive. In 1905, a young patent clerk named Albert Einstein published a paper explaining that the jittery dance was caused by the impacts of individual water molecules. This was one of the first powerful pieces of evidence for the existence of atoms. Brownian motion was our first clue. It was the first time we could see that a seemingly calm and still fluid was, in fact, a chaotic swarm of particles in perpetual motion. It revealed that beneath the surface of tranquility, there is a deep and abiding restlessness to the universe. The dance of solids, a universe in a crystal. A fluid like water is a hive of activity. But what about a solid? What about the rock that sits, unmoved, for centuries? Surely, that is still. This is where the illusion becomes even more profound. To understand it, we need to zoom in, far past what Robert Brown could have ever dreamed of seeing. We need to go down to the level of atoms. Imagine a solid, like a crystal. At the atomic level, it is not a continuous block. It is a highly ordered, tightly packed structure of atoms. A crystalline lattice. Each atom has its designated spot in this grid, held in place by powerful bonds to its neighbors. From a distance, this structure appears rigid and static. But if we could see an individual atom, we would find it is anything but still. It is vibrating. Think of it as a perfectly ordered crowd of people, where everyone is standing in their assigned spot, but every single person is uncontrollably trembling in place. Each atom is trapped in what physicists call a potential well, created by the forces of the atoms around it. Imagine an atom as a marble sitting at the bottom of a bowl. It can't escape, but it has room to roll around. Now, imagine this bowl is constantly being shaken. The marble would be rattling around its center point ceaselessly. This is the life of an atom in a solid. These atoms are oscillating back and forth hundreds of trillions of times per second. There are specific ways they can vibrate, known as vibrational modes. They can stretch, bend, twist, and rock. A complex solid has a whole orchestra of these vibrations happening simultaneously, creating a symphony of motion that is the true, hidden nature of the object. So, what is driving this unending dance? The answer is the very thing we call heat. The engine of motion, temperature and absolute zero. We have an intuitive idea of temperature. This coffee is hot, this ice is cold. But in physics, temperature is not a property of a single atom. Temperature is motion. More specifically, the temperature of an object is a measure of the average kinetic energy, the energy of motion, of its atoms. When you touch a hot stove, the feeling of hot is simply the transfer of immense vibrational energy from the atoms in the metal to the atoms in your fingers. Conversely, cold is simply the relative absence of that motion. The atoms in an ice cube are still vibrating, but much less energetically than the atoms in your warm finger. When you touch it, the faster atoms in your finger transfer their energy to the slower atoms in the ice. Your atoms slow down, and your brain registers this loss of energy as the sensation of cold. This leads to a quiet question. What happens if you keep making something colder? If you keep removing energy, do the atoms slow down? And if they do, is there a point where they stop moving altogether? This thought experiment leads us to a fundamental concept: absolute zero. As you cool a substance, its atoms vibrate less. For water, at 100 degrees Celsius, the molecules fly around as steam. As you cool it, they condense into liquid. Cool it to 0 degrees Celsius, and they lock into a fixed crystalline lattice, ice. But even in the ice, they are still vibrating. If you continue to cool that ice, the vibrations become smaller. Scientists in the 19th century calculated that there must be a lowest possible temperature. A point where all the heat energy that can be removed has been removed. This is absolute zero. 0 Kelvin, which is minus 273.15 degrees Celsius. Classically, this is the point of perfect stillness. The theoretical temperature at which all atomic motion ceases. For a long time, this was thought to be the ultimate end state of matter. Stillness, finally achieved. There's just one problem. The universe, at its most fundamental level, follows the counterintuitive rules of quantum mechanics. And according to quantum mechanics, true stillness is, and always will be, impossible. The quantum prohibition, Heisenberg's uncertainty principle. To understand why stillness is forbidden, we have to enter the quantum realm. Our guide here is the physicist Werner Heisenberg. In 1927, he formulated one of the most profound principles in all of science, the uncertainty principle. In our everyday world, we assume we can know the exact position of a car and its exact speed at the same instant. But Heisenberg discovered that at the quantum scale, this is not the case. The principle states there is a fundamental limit to how well we can know certain pairs of properties of a particle at the same time. The most famous pair is position and momentum. The more precisely you measure a particle's position, the less precisely you can possibly know its momentum. And conversely, the more you know its momentum, the fuzzier its position becomes. This isn't a limitation of our measuring instruments. It's not because our rulers are clumsy. The uncertainty is an inherent, baked-in property of the universe itself. The very concepts of an exact position and an exact momentum simply don't have meaning at the same time. So, what does this have to do with stillness? Let's return to our atom at absolute zero. If that atom were to become perfectly still, it would mean we know two things with absolute certainty. Its position would be perfectly defined, at its fixed point in the crystal lattice. And its momentum would be perfectly defined, exactly zero. But Heisenberg's uncertainty principle forbids this. You cannot know both the position and the momentum with perfect accuracy. If the momentum is exactly zero, then its position must be infinitely uncertain. If its position is perfectly known, its momentum must be infinitely uncertain. To have both be perfectly known would violate a fundamental law of the cosmos. This means that even if you remove all the thermal energy from a system, even if you cool it down to the impossible to reach limit of absolute zero, the atoms within it must continue to move. They are forbidden from stopping. This minimum, unavoidable motion is called zero-point energy. The energy of nothing, zero-point energy. The idea of zero-point energy is one of the most quietly profound predictions of quantum mechanics. It is the lowest possible energy a system can have, and that energy is not zero. It is the energy that remains when you've taken everything else away. Think back to our atom in the crystal lattice. the marble in the bowl. As we cool it, the shaking of the bowl gets weaker. But as we approach absolute zero, we find that even if the bowl stops shaking entirely, the marble inside can't settle down. It must continue to jiggle. This isn't thermal motion from heat. It's a purely quantum mechanical effect, a jitter enforced by the laws of uncertainty. We see the effects of this in the real world. Take the element helium. Every other substance, when cooled enough at standard pressure, will freeze solid. But helium is unique. Even if you cool it all the way down toward absolute zero, it doesn't freeze. It becomes a superfluid. The thermal vibrations are gone, but the zero-point energy, the mandatory quantum jiggle of the helium atoms, is still so significant that it prevents them from locking into a solid lattice. The atoms are too restless, too fundamentally uncertain, to freeze. But the concept gets even stranger. This energy also applies to empty space itself. According to quantum field theory, a perfect vacuum is not empty at all. It is a roiling sea of energy. The fields that make up the universe, like the electromagnetic field, are also subject to the uncertainty principle. They cannot have a value of exactly zero everywhere. This means that even in the darkest, coldest void, there is an underlying hum of energy. Out of this energy, pairs of virtual particles constantly burst into existence, only to annihilate each other a moment later. The vacuum is a tempest of these fleeting ghosts. Their effects are measurable, subtly shifting the energy levels of atoms and creating a tiny force between two plates in a vacuum, known as the Casimir effect. The foundation of everything, the very fabric of spacetime, is never still. The electron's cloud, redefining the atom. So far, we've focused on the vibration of whole atoms. But the story continues as we dive inside the atom itself. For a century, the popular image of an atom has been a kind of miniature solar system, with electrons orbiting a nucleus like planets. It's a simple and appealing picture. And like many simple pictures, it gives way to something more subtle and strange. The reality, dictated by quantum mechanics, is far more bizarre. An electron in an atom does not follow a path. It doesn't have an orbit. We can never know where an electron is inside an atom. The best we can do is describe a region of space where it is likely to be found. This region is called an orbital, a three-dimensional cloud of probability. Imagine a single firefly in a dark room, blinking on and off very rapidly. If you took a long exposure photograph, you wouldn't get a sharp picture of the firefly, but a ghostly cloud showing all the places it had been. The brightest parts would be where it spent most of its time. An electron orbital is like that probability cloud. The electron's position is fundamentally smeared out over the entire volume of the orbital. It exists as a wave of probability. The electron is not a planet orbiting a sun, it's a ghost haunting a house. And again, the uncertainty principle is the law of the land. If an electron were to fall into the nucleus and stop, its position and momentum would both be known. That's not allowed in the quantum world. The electron's existence as a probability cloud is a direct consequence of this. It's confined by the nucleus, but its inherent uncertainty forces it to occupy a larger space. This constant, probabilistic motion is what gives atoms their size. The reason the world is not a soup of infinitesimally dense points is because electrons refuse to be pinned down. So, every atom is a composite of this unending motion. A nucleus vibrating due to its own zero-point energy, surrounded by a shimmering cloud of electron probabilities that are themselves a manifestation of fundamental motion. The universe's subtle exception, quantum tunneling. The fact that particles exist as fuzzy waves of probability leads to one of the most consequential phenomena in physics, quantum tunneling. It allows particles to do what should be impossible, and it's the reason we are here to talk about it. Imagine throwing a ball against a solid brick wall. Classically, unless it has enough energy to break through, it will bounce back every time. Now, let's shrink that ball to a quantum particle, like a proton in the core of our Sun. The temperatures there are immense, but even so, the protons don't have enough kinetic energy to overcome their mutual repulsion and get close enough to fuse. According to classical physics, they should just bounce off each other forever. The Sun should not shine. But they don't just bounce. Because a proton is a wave of probability, its location isn't perfectly defined. Most of its probability cloud is on one side of the repulsive barrier. But a tiny, faint part of that cloud extends through the barrier and exists on the other side. This means there is a small, but non-zero, probability that the proton will suddenly be found on the far side of the wall, without ever having had the energy to go over it. It has tunneled through a region that was classically forbidden. This is how the Sun works. Protons in the Sun's core are constantly tunneling through each other's repulsive barriers. Every so often, two of them will get close enough for the strong nuclear force to take over and bind them together. This is the first step of nuclear fusion. It's this quiet, probabilistic bending of the rules that powers every star. Without the inherent motion and uncertainty of the quantum world, the universe would be dark and cold. This phenomenon is essential for modern electronics. It underpins everything from radioactive decay to the chemical reactions that make life possible. It all stems from the same core truth. Nothing is ever in one place, and nothing is ever truly still. Conclusion. The symphony of a stone. Let's go back to where we started. To that simple object, the rock, the table, your hand. That seems so perfectly still. Now, we can see it with new eyes. We can see it for what it truly is. It is not a silent, static thing. It is a symphony of motion. At the highest level are the vibrations of its atoms, a chorus of trillions of particles oscillating in place, their kinetic energy creating the temperature of the object. Beneath that, there is a deeper rhythm, the unceasing hum of zero-point energy. A purely quantum motion that persists even in the theoretical cold of absolute zero, a fundamental tremor enforced by uncertainty. And within each of those vibrating atoms is another layer of movement, the shimmering clouds of electrons, which are not particles in orbit but waves of probability, their very existence a denial of stillness. Everything is connected through this motion. The rock is connected to the ground it rests on through the transfer of vibrations. It's connected to the Sun, which only shines because its particles refuse to stay put. It's even connected to the empty space around it, which we now know is a bubbling cauldron of energy. There's also something quietly humbling about this. An object we can hold in our hand contains a universe of motion that challenges our deepest intuitions. It reminds us that our perception is not the final word on reality. Stillness, we now know, is not the absence of motion. True stillness doesn't exist. There is only motion, in a myriad of beautiful and complex forms, from the slow drift of galaxies down to the unending, quantum jitters of the void. Our world is not a collection of static things, but a single, interconnected, and eternally vibrating whole. The universal lie about standing still. Take a quiet moment and look at the world around you. Perhaps you are sitting still. A book on your desk, a mug beside it, the chair you occupy, they all appear to be the very definition of at rest. They are not moving, or so it seems. But what if this idea of standing still is a kind of universal lie? A gentle, persuasive illusion our senses have accepted for our entire lives. In the next few minutes, we will quietly peel back these layers of reality. We will see that the book on your desk, and you, are moving through the vastness of space at speeds that are difficult to grasp, part of a complex and beautiful cosmic motion. This is not a metaphor. It is physics. And by the end of this journey, the way you think about standing still may change forever. The illusion of rest. Let's begin with that book on your desk. It feels like one of the most stationary objects imaginable. If asked to define rest, you might simply point to it. In the language of classical physics, you would not be entirely wrong. An object is considered at rest when its position does not change over time relative to its immediate surroundings. The book's position isn't changing compared to the desk, the walls, or the floor. From the point of view of your room, the book is perfectly, peacefully still. But that small phrase, relative to, is the key that unlocks the entire mystery. It is the loose thread that, when pulled, gently unravels the whole concept of an absolute, universal stillness. Imagine you pick up the book and walk out of the room. From the room's perspective, the book is now in motion. But from your perspective, as you carry it, the book is still at rest relative to you. You are both moving together. This simple idea introduces one of the most fundamental concepts in all of physics: the asterisk reference frame. A reference frame is essentially a point of view, a set of coordinates from which the world is observed. Your room is one reference frame. You, as you walk, become another. The lie of standing still is not that things are incapable of being at rest. They can be. The lie is the quiet assumption that there exists a single, universal, absolute frame of stillness, against which all other motion could be measured. For centuries, humanity assumed Earth was that absolute frame. We saw ourselves as the unmoving center of everything, the ultimate definition of stationary. But as we began to look at the stars with a more questioning gaze, we realized our planet was not the quiet, stable stage we had imagined. It was the first step on a much grander, much faster cosmic journey. The book on your desk, resting so peacefully in the small reference frame of the room, is about to have its reality gently expanded. Because that room, that desk, and you are all sitting on a giant, spinning world. The cosmic dance. Layer 1, Earth's spin. The first layer of our cosmic motion is the one happening right beneath our feet. Our planet, Earth, is in a constant state of rotation on its axis. It completes one full spin about every 24 hours, giving us our cycle of day and night. This might be a fact learned in grade school, but have you ever truly considered the speed involved? The Earth's circumference at the equator is roughly 40,075 kilometers. To cover that distance in 24 hours, a point on the equator must be moving at a speed that is difficult to reconcile with our own experience. The math works out to roughly 1,674 kilometers per hour, or about 1,040 miles per hour. Let that number settle for a moment. 1,040 miles per hour. That's faster than the speed of sound. Right now, if you live near the equator, you are moving through space at supersonic speeds, just by being on this planet. Your book, your desk, everything around you, is moving at that same speed. Think of it like being on a planetary scale merry-go-round, moving with perfect smoothness. The further you are from the center of rotation, the poles, the faster you are moving. Someone at the North or South Pole is, for all practical purposes, just spinning in a tight circle, their speed nearly zero. But someone in a city near the equator is getting the full ride. If you're in a mid-latitude city like London or Tokyo, your speed is a bit less, perhaps around 1,100 to 1,300 kilometers per hour, because the circle you trace each day is smaller. But it's still a remarkable velocity. So, why don't we feel it? Why isn't a constant wind blasting us? The answer lies in the insights of Galileo and Newton. You don't feel it because everything is moving with you. The ground, the building you're in, and the air in the atmosphere are all carried along at the same constant velocity. It is similar to being in a car traveling at a steady 60 miles per hour. If you close your eyes, you do not feel the motion. If you toss a ball in the air, it comes straight back down to your hand. It doesn't fly to the back of the car. This is because the ball, the air in the car, and you already possess that forward motion. The book on your desk is not still. It's moving at hundreds of miles per hour. It just appears still because its reference frame, the room, the Earth, is moving right along with it. We have just peeled back the first layer of the illusion, and already the idea of stillness is beginning to soften. But this is just the beginning. This spinning motion is nested inside another, even faster one. The cosmic dance. Layer 2, Earth's orbit. As our planet spins, it is also moving through the solar system in its annual journey around the Sun. This is the second layer of our cosmic dance, Earth's orbital motion. We all know it takes about 365 days for the Earth to complete one orbit. But again, the sheer velocity of this journey is something we rarely pause to contemplate. Earth's orbit is not a perfect circle, but it is close. The total distance our planet travels in a single year is an immense 940 million kilometers, or about 584 million miles. To cover that distance in 1 year, our planet, and everything on it, must move at an average speed of about 107,000 kilometers per hour, roughly 67,000 miles per hour. That is about 30 kilometers per second. It's a speed that is difficult to hold in the mind. At 67,000 miles per hour, you could travel from New York to Los Angeles in under 3 minutes. This speed dwarfs the rotation of the Earth. It's about 65 times faster than the rotational speed at the equator. So, that book on your desk is not just spinning at up to 1,000 miles an hour. It is also, at the same time, moving around the Sun at 67,000 miles per hour. It is doing both, right now. And once again, we are completely unaware. We feel nothing. The reason is the same as before: inertia and the consistency of motion. We are in the system, moving with the system. The Sun's gravity holds our entire planet in a smooth, consistent orbit. There is no sudden acceleration or deceleration to jolt us. The journey is so incredibly steady that we cannot perceive it without looking outside our reference frame, by observing the changing positions of the other planets and the distant stars. For early astronomers, this was a difficult point. If the Earth were truly moving at such a speed, opponents of the Sun-centered model argued, shouldn't we be left behind? If you jump in the air, shouldn't the Earth move out from under you? This is where the profound insights of Galileo become so important, which we must now explore to truly grasp the physics behind this quiet, grand illusion. Introducing relativity and reference frames, the physics. To understand why we are so unaware of our multi-layered, high-speed journey, we need to formalize the concepts we have been touching upon. This brings us to the heart of classical mechanics, first laid down by Galileo Galilei and later Sir Isaac Newton. The core idea is what physicists call the asterisk principle of Galilean relativity. It states that the laws of mechanics are the same for any observer moving at a constant velocity. A reference frame moving at a constant velocity is called an asterisk inertial reference frame. Galileo explained this with a beautiful thought experiment. Imagine you are in a windowless cabin below the deck of a large ship, sailing on a perfectly smooth sea at a constant speed. Inside the cabin with you are flies, a bowl of fish, and a bottle dripping water into a container. Galileo reasoned that as long as the ship's motion is uniform, you will discover not the least change in all the effects named. The flies will buzz equally in all directions, the fish will swim freely, and the water will drop straight down. From within this cabin, this inertial reference frame, there is no experiment you can perform to tell whether the ship is moving or standing still. This is a profound statement. It means there is no privileged, at rest, state. Your experience inside the smoothly moving ship is physically indistinguishable from your experience on what you perceive as solid, unmoving ground. Both are inertial reference frames. Now we can connect this to the old argument against a moving Earth. When you jump, the ground does not fly out from under you because you, like the water dripping on the ship, already possess the Earth's velocity. You are moving at 67,000 miles per hour before you jump, while you jump, and after you land. Your jump is a small, additional motion on top of a much larger, shared motion. Relative to the Earth, you just go up and down. This tendency of an object to maintain its state of motion is what Newton codified in his first law of motion, also known as the law of inertia. An object at rest stays at rest, and an object in motion stays in motion at the same speed and in the same direction, unless acted upon by an external force. This is the secret. We don't feel the Earth's spin or its orbit because of inertia. We are already in motion, along with the entire planet and its atmosphere. There is no external force pushing against us to reveal this motion, no cosmic friction slowing us down. To us, within our shared reference frame, everything feels perfectly still. The only way to know we are moving is to look to other reference frames, the sun, the planets, the distant stars, and measure our changing position relative to them. Stillness is not an absolute property. It is a relationship between an object and an observer. By accepting this, we have the tools to zoom out even further, to more immense layers of motion. The cosmic dance. Layer 3, the solar system's journey. We have established that our book is spinning with the Earth and orbiting the Sun. But the Sun itself is not a stationary anchor in the cosmos. Our star, along with its entire family of planets, is also on an epic journey. Our whole solar system is in orbit around the center of our home galaxy, the Milky Way. The Milky Way is an immense spiral galaxy of hundreds of billions of stars. Our Sun is located in one of its spiral arms, about 2/3 of the way out from the galactic center. And just as the Earth is bound to the Sun is gravitationally bound to the supermassive black hole and the concentrated mass at the galaxy's core. This forces our solar system into a vast, sweeping orbit. The speed of this galactic journey is almost beyond our everyday comprehension. Our solar system travels at an average speed of approximately 792,000 kilometers per hour, about 490,000 miles per hour, which is around 220 kilometers per second. Let us pause to absorb that number. Nearly 500,000 miles per hour. This motion is over 7 times faster than Earth's orbit around the Sun, and hundreds of times faster than Earth's rotation at the equator. So, let's update the status of our still book. It is spinning at up to 1,040 miles per hour. It is orbiting the Sun at 67,000 miles per hour. And it is simultaneously orbiting the center of the Milky Way at 490,000 miles per hour. Even at this incredible speed, the galaxy is so vast that it takes our solar system about 225 to 240 million years to complete a single orbit. This is a galactic year. This means the last time our solar system was in this part of the galaxy, the first dinosaurs were just beginning to appear on Earth. All of human history has taken place in a tiny fraction of this single cosmic lap. And, of course, the principle of inertia holds true once again. We do not feel this motion. There is no sense of speed. We are deep inside the system, moving along with it, held in the gravitational embrace of our galaxy. By now, the idea of that book being at rest should seem almost curious. It is a participant in a multi-layered, high-velocity cosmic ballet. But there is one final, grand layer to add. The cosmic dance. Layer 4, the galaxy's motion. We've zoomed out from the room to the planet, from the planet to the solar system, and to the galaxy. It is tempting to think this must be the end. But the universe is more dynamic than that. Our Milky Way galaxy is not stationary. It, too, is moving. But moving relative to what? If everything is in motion, how do we find a landmark? Modern cosmology provides an incredible answer. The cosmic microwave background or CMB. The CMB is the faint, residual afterglow of the Big Bang, radiation that fills the entire universe. It was released about 380,000 years after the universe began. This ancient light provides the ultimate reference frame, a backdrop against which we can measure the motion of everything else. When we observe the CMB, we find that it is astonishingly uniform. However, it is not perfectly uniform. Scientists have detected a very slight temperature variation. The CMB appears slightly warmer, blue shifted, in one direction of the sky, and slightly cooler, red shifted, in the opposite direction. This is the cosmic version of the Doppler effect, the same principle that makes a siren sound higher in pitch as it approaches and lower as it moves away. This temperature shift tells us that we are moving through this ancient light. And the speed is the most staggering of all. After accounting for the motions of the Earth and the Sun, astronomers have calculated the velocity of our entire Milky Way galaxy. We are being pulled by the gravity of other massive galaxy clusters, like the Great Attractor. The result is that the Milky Way and its local group of galaxies are moving through the universe, relative to the CMB, at a speed of about 2.1 million kilometers per hour, 1.3 million miles per hour, which is about 600 kilometers every second. This is the final, grandest motion we can currently measure. 1.3 million miles per hour. That book on your desk, which began our journey sitting so innocently still, is caught in this colossal cosmic current. It spins, it orbits, it revolves around the galaxy, and the entire galaxy is being flung through the universe. The illusion of stillness has now been completely, and quietly, dismantled. Putting it all together, the vector sum. We have uncovered four fundamental layers of motion. Earth's spin, its orbit around the Sun, the solar system's orbit in the galaxy, and the galaxy's own motion through the universe. Now, a crucial point. To find the true velocity of the book, we cannot simply add these speeds together. Motion is a asterisk vector. It has both a speed and a direction. To find the true velocity of our book, we would have to perform a complex vector addition, accounting for the different directions of all these movements. The axis of Earth's spin is tilted. The plane of Earth's orbit is at a different angle. The plane of our solar system's journey around the galactic center is tilted yet again. And the direction of our galaxy's drift through the cosmos is something else entirely. Imagine trying to track a single, tiny fly in a glass box. The box is on a spinning carousel, which is on the back of a truck driving in a large circle, and that entire racetrack is on a bullet train. The fly's final path would be an incredibly complex, looping, spiraling trajectory. That fly is the book on your desk. Its motion is a beautiful, intricate superposition of all these cosmic movements. The velocity of its spin is constantly changing direction. The velocity of its orbit points somewhere new every day of the year. The velocity of its galactic journey is on a timescale of millions of years. And its cosmic drift is on the grandest scale of all. This is the complex cosmic dance we spoke of. The simple state of standing still is, in reality, this extraordinarily complex state of combined velocities. When you sit in your chair, you're tracing a path through the universe of almost unimaginable intricacy. The philosophical implications and the nature of reality. So, what does this all mean? We have dismantled the idea of stillness, replacing it with a cascade of immense speeds. The journey from Galileo's ship to the cosmic microwave background reveals a fundamental truth. There is no absolute rest. Every statement about motion is, by necessity, a statement of relative motion. Are you moving? The only correct response is another question. Relative to what? Relative to your chair, you are at rest. Relative to the center of the Earth, you are moving at hundreds of miles per hour. Relative to the Sun, you are moving at tens of thousands of miles per hour. Relative to the center of the galaxy, you are moving at hundreds of thousands of miles per hour. Relative to the afterglow of creation itself, you are moving at over 1 million miles per hour. None of these statements is more true than another. They are all equally valid descriptions of your motion from different reference frames. The universe does not provide a master anchor point, a universal, "you are here," sign that is truly fixed. This very concept, the relativity of motion, was the bedrock upon which Albert Einstein built his own revolutionary theories. He took Galileo's principle and asked what would happen if something, like a beam of light, appeared to have the same speed in all inertial reference frames. That question led him to rewrite our understanding of space, time, and gravity. We began with a quiet mystery, the lie of standing still. We took a common-sense observation and found it to be an illusion born of perspective. The solution was a progressive unveiling of that perspective. By changing our reference frame, we discovered a deeper, more dynamic reality. There is something quietly humbling about it. This journey changes how we see our place in the cosmos. It replaces a static existence with one of incredible dynamism. The feeling of being stationary is a local comfort, a simplification that allows us to navigate our immediate world. But it masks a magnificent truth. We are all cosmic voyagers. Every moment of your life, whether you are running a marathon or are fast asleep, you're participating in this grand journey through space-time. Conclusion. From a book on a desk to the faint echo of the Big Bang, we have seen that stillness is little more than a trick of perspective. It is an agreement between you and your surroundings to ignore the colossal, intertwined motions carrying you through the cosmos. The feeling of being perfectly still is an illusion. In reality, you are on the most epic journey imaginable, a silent passenger on spaceship Earth, which is itself a passenger in the starship of the solar system, which is a passenger on the galactic cruiser Milky Way as it sails the cosmic ocean. So the next time you sit down and feel utterly motionless, take a moment. Remember the spin, the orbit, the galactic swirl, and the cosmic drift. And enjoy the ride. If this quiet exploration into the nature of reality helped you see things in a new way, consider liking the video and subscribing to the channel. And please feel free to share in the comments what other everyday concepts you think we should explore next. How you can be moving and still at the same time. Right now, I'm walking forward. But at the same time, I'm not moving at all. And no, this isn't some kind of trick. It's a real-life demonstration of a fundamental truth about our universe. You are never truly still. By the end of this video, you'll understand exactly why. This simple paradox, which you can experience in any major airport, holds the key to one of the most profound principles in all of physics. It's an idea that governs everything from a person strolling through a terminal to the majestic dance of galaxies across the cosmos. We're about to take a journey that will challenge your very definition of still. We'll start with a simple, everyday scenario and, step by step, zoom out until we're looking at our own place in the universe in a completely new light. By the time we're done, the solid ground beneath your feet might not feel so solid anymore. You'll see that motion isn't a simple fact, but a complex and beautiful relationship. So, get ready to have your perspective shifted, because the world is in constant, frantic motion, even in its quietest moments. Picture it. You're at the airport. That familiar non-place of hurry up and wait. The air hums with the low rumble of jet engines and the chime of boarding announcements. You've just cleared security, and of course, your gate is at the other end of the terminal. But luckily, you see it. The moving walkway, a ribbon of black rubber gliding smoothly through the crowd. You step on, and a gentle push takes over. Now, let's say your friend is standing on the stationary floor right next to the walkway. You decide to have a little fun. You turn around and start walking backward, against the walkway's flow. You carefully match your pace, keeping your eyes on your friend. And then, something weird happens. As you keep walking, putting one foot in front of the other, your friend sees you, just hovering. You're walking, but you're perfectly still, so much so that you could reach out and hold a high five for 10, 20, even 30 seconds, all while your legs are pumping away. How is that possible? How can you be actively walking, yet completely motionless? This isn't a glitch in the matrix. It's a perfect demonstration that the question, "Am I moving?" is always incomplete. The only question that makes sense is, "Am I moving relative to what?" The airport walkway, unpacking the paradox. Let's break this airport illusion down piece by piece, because once you get this, everything else clicks into place. The secret is that there isn't just one speed to think about. There are several, all happening at once, and it all depends on your point of view. First, let's take your perspective on the walkway. As soon as you step on, you feel that little lurch of acceleration. You're part of its system now. To make it clear, let's use a number. Say the walkway moves at a steady 3 miles per hour relative to the airport floor. As you stand there, you glide past the stores and other gates. Now, you decide to walk. Your muscles tense, you push off the belt, and you start moving. From your own perspective, it feels like you're walking at a normal pace. Let's call it another 3 miles per hour. The rubber surface is scrolling by under your shoes. If you were to drop a sticker on the belt, you'd see it move away behind you. From your point of view, in your little moving world, you are without a doubt in motion. Okay, now let's jump into your friend's shoes. They're standing still on the solid, unmoving floor of the terminal. Their point of view is what we can call the ground frame. They're rooted to the building. What do they see? They see the whole walkway flowing past them like a river of rubber at 3 miles per hour. They see you step on and get carried along. But then, they watch you turn around and start walking in the opposite direction. This is where the magic of relative motion happens. The walkway is trying to carry you forward at 3 miles per hour. Your body, by walking, is trying to move you backward at 3 miles per hour. Let's think of it as simple math. The walkway gives you a plus 3 miles per hour forward velocity. Your walking adds a minus 3 miles per hour backward velocity. For your friend, who sees both things happening at once, the result is simple. Plus 3 and minus 3 equals 0. Relative to your friend, your velocity is 0. You are walking, but you're going nowhere. You're a living, breathing balanced equation. You can see the people standing behind you on the walkway getting closer, while the people in front get farther away. You are absolutely moving relative to everyone else on the walkway. But you are perfectly still relative to your friend, the terminal, and the entire airport. This reveals a startling truth. You can have multiple, completely different speeds at the exact same time. Your speed relative to the walkway is 3 miles per hour. Your speed relative to the airport is 0 miles per hour. Both are 100% correct. Neither is more true than the other. They are just different ways of describing the same event from different points of view. To really lock this in, let's flip the experiment. What if you walk with the walkway? It's already giving you a 3 miles per hour boost relative to the ground. Now, you start walking forward at your normal 3 miles per hour pace. To you, it just feels like a regular walk. But to your friend on the stationary floor, it's a totally different picture. They see the walkway's speed and your walking speed combine. Your 3 miles per hour from the walkway adds to your 3 miles per hour of walking, and you blaze past them at a combined 6 miles per hour. You're walking at a normal pace, but you're effectively jogging. And just like that, the whole idea that an object has one single, true, speed falls apart. Speed isn't something an object has. It's a property of the asterisk relationship between two objects. Introducing the frame of reference. So, what does this all mean? How can one person be moving at 0 miles per hour, 3 miles per hour, and 6 miles per hour at the same time without breaking the universe? Well, the truth is, this idea actually upholds one of the most fundamental principles of physics. It's because we've been using a concept that physicists call a frame of reference. A frame of reference sounds technical, but it's an idea you use intuitively every single day. It's just a point of view, a system you use to measure motion. In our airport story, we weren't just dealing with two people. We were dealing with at least two different frames of reference. The first was the moving walkway itself. When you're on it, you're in its system. For you, the most natural way to measure your own motion is against the belt you're standing on. In this walkway frame, your speed was your walking speed, 3 miles per hour. From this perspective, the airport terminal actually seems to be moving backward at 3 miles per hour. Your friend wasn't stationary, they were gliding past you in the opposite direction. It sounds weird, but from the walkway's point of view, it's 100% correct. The second frame of reference was the airport floor, where your friend stood. This is what's often called a stationary frame, or ground frame, because, for most of us, the ground feels like it's still. From this ground frame, the measurements were totally different. In this frame, the walkway was the thing moving, and your walking speed was either added to or subtracted from it. It was from this frame that your speed came out to be 0 miles per hour or 6 miles per hour. The paradox of being both moving and still completely vanishes the moment you ask the right question. Relative to which frame of reference? Let's push this one step further. Imagine, while you're doing your stationary walk, a baggage cart zips by on the tarmac outside the window, going 15 miles per hour in the same direction as the walkway. The driver of that cart is in a third frame of reference. What does the driver see? From their 15 mph moving world, the entire airport terminal looks like it's flying backward at 15 miles per hour. Your stationary friend is also zipping backward in their view. And you? Since your speed relative to the terminal is 0, from the cart driver's perspective, you are also moving backward at 15 miles per hour. So now, at the same instant, you have 3 totally valid speeds. 3 miles per hour, relative to the walkway. 0 miles per hour, relative to the airport. Minus 15 miles per hour, relative to the baggage cart. This is the big, aha moment. There's no such thing as an absolute, true, speed. Any speed is meaningless until you define the frame of reference you're measuring from. The universe doesn't have a default, still, position. Everything is just moving relative to everything else. This idea, first spelled out by Galileo hundreds of years ago with his thought experiment on a smoothly sailing ship, is known as the principle of relativity. And we just proved it with a moving walkway. Expanding the analogy, trains and rivers. This isn't just a fun airport trick. It's a rule that governs everything, everywhere. To really see its power, let's leave the airport and hop on a train. Imagine you're on a high-speed train, gliding along the tracks at a constant 100 miles per hour. It's so smooth that if you close the blinds, you might forget you're moving at all. You're at a table and decide to pour a glass of water. The water falls in a perfect, straight line into the glass. It doesn't fly backward and splash against the wall. You can toss a coin in the air, and it goes straight up and falls right back into your hand, just like it would in your kitchen. Why? Because you, the water, the coin, and the air in the car are all inside the same frame of reference, the train frame. Everything inside is already moving forward at 100 miles per hour. When you pour the water, it already has that forward velocity. As it falls, it keeps moving forward, so relative to you, its only motion is downward. The normal feeling you have inside the train is just the feeling of being at rest in your frame of reference. But now, let's switch frames. What does someone standing on the platform see? They don't see the waterfall in a straight line. They see the train blur past at 100 miles per hour. If they could track the water, they'd see it move forward at 100 miles per hour while it falls downward. From their perspective, the water traces a long, curved path called a parabola. Once again, 2 completely different descriptions of the same event. Inside the train, the coin goes up and down. Outside, it travels in a wide arc. Which is right? Both. They're just observations from 2 different, equally valid frames of reference. This gets even cooler when we add another dimension. Let's head to a river. Imagine you want to swim from one side of a wide river directly to a point on the opposite bank. Let's call your start point A and your goal point B. The river, however, has a strong current flowing downstream. You dive in, aim your body right at point B, and start swimming. What happens? From your perspective, you're cutting through the water, heading straight for your goal. But someone watching from the riverbank, Our ground frame sees something else. They see your swimming motion across the river, but they also see the current carrying you downstream. The combination of the two results in a diagonal path. You'll end up on the other side, but way downstream from where you wanted to be. So how do you actually get to point B? To counteract the river's flow, you can't aim where you want to go. You have to aim upstream. You angle your body against the current. Now, part of your swimming effort pushes you across the river, and part of it pushes you upstream. If you get the angle just right, the upstream part of your swimming cancels out the downstream push of the current. To the observer on the bank, the sideways battle is invisible. The only motion they see is your steady progress straight across the river, from A to B. Think about how that feels. To move in a straight line for an outside observer, you have to constantly swim at an angle, fighting a current you can't see. This is the everyday reality for pilots in crosswinds and boat captains in currents. They have to constantly account for the motion of their frame of reference, the air or the water, to control their motion relative to the ground. The cosmic zoom out. You are never truly still. We started on an airport walkway, and now it's time to go back to that bold statement from the beginning. You are never, ever truly still. Right now, you probably feel stationary. You might be sitting in a chair, feeling solid, stable, and unmoving. But this feeling of stillness is a profound illusion, created because you, your chair, and everything around you are on a series of incredible, high-speed journeys together. Let's start our cosmic zoom out. You may be still relative to the floor, but that floor is part of a planet that's constantly spinning. To make one full rotation in 24 hours, the Earth's surface at the equator has to move at over 1,000 miles per hour, or about 1,670 kilometers per hour. Right now, you are hurtling through space faster than a commercial jet. Why don't you feel it? For the same reason you can pour water on a 100 mph train. You, the chair, the building, and the very air you're breathing are all part of the same rotating system. You're all moving at 1,000 miles per hour together, so your speed relative to the Earth's surface is zero. But that's just the first layer. Let's zoom out. The Earth isn't just spinning, it's on a massive, year-long orbit around the Sun. To complete that orbit, our planet is moving at a mind-boggling speed. Your current speed, relative to the Sun, is about 67,000 miles per hour. That's nearly 30 kilometers every single second. You are riding a planetary spaceship moving almost 100 times faster than a speeding bullet, and you don't feel a thing. So, is the Sun the ultimate stationary object? Not even close. Zoom out again. Our Sun is just one of hundreds of billions of stars in the Milky Way galaxy. And our entire solar system is orbiting the galactic center. This journey is so vast it takes over 200 million years to complete just one lap. The speed required is staggering. Relative to the center of the Milky Way, you, the Earth, and the whole solar system are moving at an average speed of 515,000 miles per hour. And we can keep going. The Milky Way itself is being pulled by gravity toward our galactic neighbor, Andromeda. Our entire local group of galaxies is drifting through space toward a massive gravitational point called the Great Attractor. This leads to a final, mind-bending conclusion. Are you still? Well, you're still relative to your chair. But you're moving at 1,000 miles per hour relative to the Earth's core. And 67,000 miles per hour relative to the Sun. And 515,000 miles per hour relative to the galactic center. The question, what is my true speed, is meaningless. It has no answer because the universe has no center, no fixed background, no absolute, still, against which all motion can be measured. There's only a web of infinite relationships, where everything moves relative to everything else. Conclusion. So, we started our journey on a simple airport walkway, puzzled by how you could be walking but going nowhere. We found the answer depended entirely on our point of view, on our frame of reference. From that one idea, we uncovered a universal principle. We saw it on trains, where a tossed coin can go straight up and in a giant arc at the same time. We saw it in rivers, where a swimmer has to aim in one direction to travel in another. And then we turned that lens back on ourselves, revealing the frantic, nested motion hidden in our quietest moments. The key takeaway is this: stillness isn't a state. It's a relationship. It's the experience of sharing a ride with your immediate surroundings. You are still relative to the earth, but the universe is a symphony of motion, and you are part of the orchestra. So the next time you're sitting somewhere, feeling perfectly, peacefully still, take a moment to remember what's really happening. Remember the layers of motion you're a part of. The spin of a planet, the orbit around a star, the grand, sweeping spiral of a galaxy through the cosmos. You're a passenger on spaceship Earth, a tireless traveler moving in a dozen different ways at once. That sensation of stillness is just the quiet calm in the heart of a magnificent cosmic storm. If this shifted your perspective on something as simple as standing still, hit that subscribe button for more journeys into the hidden rules that shape our reality. And now I have a question for you. What's another everyday situation that has always felt like a little physics puzzle to you? Let me know in the comments below. Why nothing in the universe can ever stop moving. A rock can rest in the palm of your hand. A car can sit parked in a driveway, its engine silent. Our world seems to be filled with things that are still. But this stillness is not what it appears to be. It is an idea that grows less and less true the closer you look. There is a point of ultimate cold, a temperature called absolute zero, where all the motion we see in the everyday world is supposed to vanish. But something strange happens on the journey there. A quiet, persistent energy reveals itself, an energy that ensures nothing in the universe is ever truly at rest. Welcome to the Sleepy Scientist. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether it's daytime or late at night, feel free to share where you're watching or listening from. For a long time, the world appeared to be a place of stillness. The chair you're in, the floor beneath you, a book on a table, they all seem to hold their position perfectly. This is the world we experience directly, a world governed by familiar rules. Motion begins with a push and ends with friction. But this sense of stillness is a gentle illusion, one that depends entirely on perspective. To peel back the first layer of this illusion, we only need to look up. The rock held so still in your hand is on a planet spinning on its axis at over 1,600 kilometers per hour. That planet is also moving around its star at a speed of nearly 107,000 kilometers per hour. The entire solar system is traveling through the Milky Way galaxy at around 828,000 kilometers per hour. The galaxy itself is moving, pulled by the gravity of its neighbors. And the whole of space is expanding, carrying everything along with it. From a cosmic perspective, stillness was never an option. But even if we could imagine all of that motion away, stop the Earth, the Sun, and the galaxies in their tracks, the rock would still not be at rest. To understand why, we have to change our view again. We have to look past the surface of the rock, past the mineral grains, and down to the atoms themselves. It is here, in the microscopic world, that the true, unending dance of the universe is revealed. And the first driver of this quiet commotion is something we feel every day: heat. We think of temperature as a measure of hot or cold. But in physics, it is something more fundamental. Temperature is a measure of how much the atoms and molecules that make up an object are moving. Every object with a temperature above absolute zero is a quiet hive of microscopic activity. The particles it's made of are in a state of constant, gentle motion. In a solid, like a piece of iron, atoms are held in a fixed, crystal structure. They are not free to wander. But they are not still. They vibrate in place, each one a tiny, resonant tremor. The more they vibrate, the higher the temperature. If we warm the iron until it melts, it becomes a liquid. The particles now have enough energy to break free from their rigid positions. They can slide past and tumble over one another. They are still close together, but no longer locked in place. Imagine a slow, crowded dance, where every participant is always in motion. If we add more heat, the liquid turns into a gas. The particles gain so much energy they fly apart, moving freely and randomly, colliding with each other and the walls of their container millions of times a second. The nitrogen and oxygen molecules in the air around you are moving at around 500 meters per second. This perpetual motion is governed by the laws of thermodynamics, which tell us that this energy, this heat, cannot be destroyed. It can only be moved somewhere else. This leads to a simple question. If heat is motion, can we remove all the heat to find perfect stillness? This question began a long, quiet search, a journey toward a theoretical point of ultimate cold, absolute zero. The idea of an ultimate cold was not always obvious. For a long time, cold was thought by some to be a substance, a fluid that flowed into things. In the 17th century, the scientist Robert Boyle began to seriously consider the existence of an absolute minimal temperature. But the real understanding of cold began to form once reliable thermometers were invented. In the early 18th century, the physicist Guillaume Montans was studying how the pressure of a gas changed with temperature. He noticed that as a gas cooled, its pressure dropped in a straight, predictable line. He then performed a thought experiment. If you kept cooling the gas, the pressure would keep dropping until it eventually reached zero. Since pressure comes from particles hitting the walls of a container, zero pressure would mean the particles had stopped moving. He made a quiet prediction: there must be a point of absolute cold. His estimate, around -240 degrees Celsius, was remarkably close. Over the next century, other scientists refined this idea. This work led to William Thomson, later known as Lord Kelvin, who in the mid-19th century calculated the point of this ultimate cold to be -273.15 degrees Celsius. He proposed a new temperature scale, one that began at this true, fundamental zero. We call it the Kelvin scale. On this scale, absolute zero is simply 0 K. The destination was now on the map. The journey to reach it became one of the great quiet adventures of physics. Scientists like James Dewar and Heike Kamerlingh Onnes developed ingenious ways to cool gases, using cycles of compression and expansion. They liquefied oxygen, then nitrogen, then hydrogen. The last frontier was helium. In 1908, Kamerlingh Onnes succeeded, liquefying helium at just 4.2 Kelvin. For a time, his laboratory became the coldest place on Earth. Since then, scientists have gotten even closer, reaching temperatures of just billionths of a degree above absolute zero. But they have never reached it. And they never will. A fundamental law of the universe, the third law of thermodynamics, states that it's impossible. As you get colder, it becomes harder and harder to remove the last bit of heat. But something more profound was discovered on this journey into the cold. Classical physics predicted that at 0 K, all motion would stop. But classical physics was wrong. As we approached this limit, we entered a new kind of world, one governed by different rules. We entered the world of quantum mechanics. And in the quantum world, stillness itself is not allowed. For centuries, our understanding of motion was based on classical mechanics, the physics of Isaac Newton. In this world, everything is predictable. If you know where an object is and how fast it's moving, you can know its future perfectly. An object can have zero momentum. It can be perfectly still. But at the beginning of the 20th century, scientists found that this picture breaks down at the scale of atoms. The world of electrons and photons is governed by a different set of rules, quantum mechanics. And one of its most fundamental rules is the Heisenberg uncertainty principle, introduced by Werner Heisenberg in 1927. The uncertainty principle states that there is a limit to how precisely we can know two connected properties of a particle at the same time. The most well-known pair is position and momentum. The more accurately you know where a particle is, the less accurately you can know its momentum, and the other way around. This isn't a problem with our tools or our methods. It is a fundamental property of the universe itself. At a quantum level, a particle doesn't have a single, exact position and a single, exact momentum at the same time. It exists as a wave of possibilities. What does this mean for trying to stop something? To be perfectly at rest, a particle would need to have a momentum of exactly zero. Not close to zero, but precisely zero. According to the uncertainty principle, if we knew the momentum with perfect certainty, that it's zero, our uncertainty about its position would have to become infinite. A particle with an infinitely uncertain position is everywhere at once and nowhere. It has no defined location. This means a particle can never be perfectly still. If it were, it would have a defined position and a defined momentum of zero, which would violate a fundamental rule of quantum reality. Even if you could remove all of its heat, all of its thermal energy, the laws of quantum mechanics themselves would force it to keep moving. It must always possess some small, residual motion. This inescapable quantum motion is called zero-point motion. And the energy that drives it has a name: zero-point energy. Zero-point energy is the lowest possible energy a quantum system can have. Classically, we would expect the lowest energy to be zero. But quantum mechanics says it is not. Because of the uncertainty principle, even at absolute zero, a system must hold on to a minimum, non-zero amount of energy that drives a constant, quiet fluctuation. This is not just a theoretical idea. Zero-point energy is real, and its effects can be seen. This quiet energy exists everywhere in the universe. According to quantum field theory, what we think of as empty space is not truly empty. It is a field of constant, simmering activity. These fluctuations can even, for tiny moments, bring pairs of virtual particles into existence, which appear from the energy of the vacuum and then disappear back into it. Empty space is filled with a universe-wide hum of energy that can never be turned off. We have never cooled anything to absolute zero, but as we get close, we see what zero-point energy does. The most famous example is helium-4. It is so light, and its atoms are so weakly attracted to each other, that even at absolute zero, its zero-point energy is enough to keep it from becoming a solid. The atoms have too much quantum jiggle to freeze. Instead, helium remains a liquid, a quantum liquid with strange properties, like the ability to flow without any friction at all. Zero-point energy is the final, unbreakable barrier to stillness. It is the universe's quiet declaration that everything must move, always. This idea of an invisible energy that keeps everything moving might sound like philosophy. But zero-point energy is a testable reality. The most direct piece of evidence is known as the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir made a strange prediction. If you take two flat, uncharged metal plates and place them parallel to each other in a perfect vacuum, extremely close together, classical physics says nothing should happen. But Casimir realized the zero-point energy of the vacuum would change things. Remember the sea of virtual particles and fluctuating fields? Those fields are made of waves of all possible wavelengths. Outside the plates, waves of every wavelength can exist. But the tiny space between the plates acts like a resonant chamber. Only waves that fit perfectly into that gap are allowed. This means there are more quantum fluctuations on the outside of the plates than on the inside. The result is a small, net pressure from the outside, pushing the plates together. This gentle, purely quantum force, born from the energy of empty space, is the Casimir effect. For decades, the force was thought to be too weak to measure. But in 1997, a delicate experiment successfully measured the Casimir force, confirming the prediction. The zero-point energy of the vacuum is real, and it has measurable consequences. It also explains subtle shifts in the energy levels of hydrogen atoms, and, as we saw, it explains why helium refuses to freeze. It is written into the fabric of reality, a constant hum that proves perfect stillness is not possible. This quantum jiggle is universal. Every atom in your body, in the device you're watching this on, in the planet beneath your feet, is subject to it. It is the floor of motion below which nothing can ever fall. We began by looking at the large-scale motion of planets and galaxies. We zoomed in to the thermal vibration of atoms. And finally, we arrived at the quantum floor of zero-point motion. Thermal motion is the chaotic dance driven by heat. Zero-point motion is the subtle tremor that remains even when all the heat is gone. Every particle in a solid vibrates because of its temperature, but even at 0 Kelvin, it would continue to vibrate with its zero-point energy. This is why electrons in an atom don't spiral into the nucleus. They occupy energy levels, and the lowest possible energy level is not zero. It is a state of minimum, but non-zero, energy and motion. This connects to a deeper idea, that everything, at its most fundamental level, is a vibration in a quantum field. So, the next time you hold a rock in your hand and see it as perfectly still, remember the hidden layers of movement. Remember the planet spinning, the solar system moving through space, the atoms vibrating with heat, and beneath it all, the quiet hum of zero-point energy, the quantum tremor that ensures nothing in the universe can ever truly stop moving. The discovery that absolute stillness is impossible represents a fundamental shift in our picture of reality. For a long time, many philosophical traditions looked for something permanent, unchanging, and absolute. Stillness was often seen as an ideal state, but modern physics shows a different picture. It tells us that the universe is not a static object. It is a dynamic, evolving process. The fundamental nature of reality is not being, but becoming. Change is not an imperfection, it is the engine of everything. Motion is not a temporary state, it is the only state. This idea can be both unsettling and beautiful. It means there is no final point of rest. But it also means the universe is endlessly creative. The constant flux of energy is what allows stars to form, life to emerge, and consciousness to consider its own existence. A universe at perfect rest would be a universe without complexity, change, or life. Our universe is alive with a quiet, constant dance of energy. The fact that nothing can stop moving isn't a flaw. It's the central feature. So, we have traveled from a simple observation of a still object, all the way down to the coldest possible temperature, and into the quantum realm. We've seen that what looks like rest is an illusion of scale. On a cosmic scale, we are in constant motion. On a thermal scale, our atoms are always vibrating. And on a quantum scale, a fundamental rule gives rise to a zero-point energy that ensures nothing can ever be truly still. But this raises a final, quiet question. If everything is fundamentally in a state of constant motion, what does that say about our perception of time? Is our sense of the flow of time simply an emergent property of this universal, unstoppable movement? Let me know your thoughts in the comments below. And if you want to keep exploring the fundamental nature of reality with us, make sure you subscribe. The impossible quest for absolute zero. Imagine a place of absolute stillness. A temperature so cold that every atom in the universe would freeze in its tracks. A cosmic basement where the chaotic dance of existence comes to a perfect, final halt. For over a century, scientists have been in a race to reach this impossible point, absolute zero. But what they found instead was a paradox at the very heart of physics, a discovery that makes true stillness a cosmic illusion. This is the story of that impossible quest. As it turns out, the temperature we feel is just motion. It's the jiggling, vibrating, and zipping around of atoms. The hotter something is, the more frantically its tiny parts dance. The colder it gets, the more sluggish they become. So, it's only logical that if you keep cooling something, eventually, all that motion has to stop, right? There must be an ultimate cold. A point of maximum chill where you can't extract any more heat, because there's no motion left to stop. This theoretical floor of the universe is called absolute zero. It sits at a frosty zero on the Kelvin scale. That's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. And that number didn't come from a sudden discovery. It was a slow realization that started with something as simple as watching a balloon shrink in the cold. Back in the 17th and 18th centuries, scientists like Guillaume Montans and later Jacques Charles noticed a strangely perfect, straight-line relationship. As you cool a gas, its volume shrinks proportionally. And if you plot that on a graph and extend the line down, way down into temperatures nobody could reach yet, it points to a startling conclusion. At minus 273.15 Celsius, the volume of any gas would shrink to nothing. Of course, a gas can't just have zero volume. Long before that, it would turn into a liquid and then freeze solid. But that line on the graph was a giant, blinking arrow pointing to something fundamental. It suggested a boundary. A point where the rules of temperature and volume just seemed to break. This wasn't just a new record to beat, it was a theoretical wall at the end of the universe's temperature gauge. In 1848, the physicist William Thomson, later known as Lord Kelvin, made it official. He proposed a new temperature scale, an asterisk absolute scale, where zero wasn't just based on something convenient like the freezing point of water. It was anchored to this ultimate limit. 0 Kelvin was absolute zero, the coldest anything could ever be. And with that, the finish line was drawn for the most extreme race in science. The quest was on, not just to get cold, but to reach the very end of cold itself. To touch the void. But as we're about to see, this isn't just a story about reaching a destination. It's about discovering that the destination isn't what we thought it was. It's a journey that would force us to throw out our old ideas and face the bizarre, ghostly rules of the quantum world. A world where stillness is forbidden, and where even at absolute zero, the universe refuses to shut up. The liquefaction wars. The path to absolute zero in the late 19th and early 20th centuries wasn't a gentle stroll. It was a brutal, high-stakes war fought in labs across Europe. A series of intense rivalries and daring engineering feats that came to be known as the liquefaction wars. The goal was simple: turn every gas into a liquid. Why? Because liquefying a gas was the best cooling tech they had. When a liquid evaporates, it sucks up a ton of heat, making things incredibly cold. If you could liquefy a gas with a really low boiling point, you could use its evaporation to cool down an even more stubborn gas until it liquefied. It was a painstaking, cascading process, a step-by-step descent into the frozen unknown. The battlefield was littered with shattered glass and the ghosts of failed experiments. Early victories came with gases like chlorine and ammonia, but the real prizes, the so-called permanent gases, were way tougher. These were the gases that had shrugged off every attempt to liquefy them with pressure alone. Oxygen, nitrogen, hydrogen, and the newly discovered, maddeningly elusive helium. At the center of this frigid conflict were two titans of cold: James Dewar in London and Heike Kamerlingh Onnes in Leiden. Dewar, a brilliant and flamboyant Scotsman, was a master of the lab. He was also fiercely secretive and competitive. His greatest contribution was an invention born from pure necessity: the vacuum-insulated flask. Today, you'd call it a thermos, but for cryogenics, the Dewar flask was a game-changer. It let scientists store ultra-cold liquids for hours, giving them time to actually run experiments. Without it, their precious liquid would boil away in minutes. Dewar scored a huge victory in 1898 when he finally conquered hydrogen. This was a massive achievement. Hydrogen liquefies at a mind-numbing 20 Kelvin, just 20 degrees above absolute zero. To get there, Dewar used liquid air to pre-cool the hydrogen, then forced it through a tiny nozzle. As the gas rapidly expanded, it cooled itself down, a process called the Joule-Thomson effect. After years of effort and taking huge risks, hydrogen is famously explosive. He did it. He was the first person to ever see a pool of liquid hydrogen. He'd reached the coldest temperatures on Earth and was now on the doorstep of absolute zero. Only one gas remained: helium. First spotted in the sun's spectrum, helium was the ultimate prize. It was incredibly rare, and its boiling point was predicted to be the lowest of all. Dewar tried to liquefy it. He used his liquid hydrogen, the coldest tool available, to chill the helium gas, but it wouldn't give in. Frustrated and with limited supplies, his attempts failed. He started to think that maybe helium simply couldn't be liquefied. Meanwhile, in the Netherlands, Heike Kamerlingh Onnes was building an empire. If Dewar was a solo artist, Onnes was an orchestra conductor. He turned his lab at Leiden University into a cold factory, an industrial-scale operation with teams of technicians all working in concert. His motto was, through measurement to knowledge. He wasn't just trying to get cold for glory. He wanted to build a stable platform to study what happens to matter at these insane temperatures. Onnes saw liquefying helium as the final key to unlocking a new frontier. He knew Dewar had failed, but he attacked the problem with methodical persistence. He got a better helium supply and built a bigger, more powerful cooling apparatus, a tangled masterpiece of pipes and compressors all designed for one purpose. The final assault took place on July 10, 1908. It was a grueling, all-day marathon. The team produced vast quantities of liquid air to cool a bath of liquid hydrogen. Finally, the purified helium gas, already chilled by the hydrogen, was sent into the final circuit. Compressed and cooled, it was released through the tiny expansion valve. For hours, nothing. The temperature dropped lower and lower, but there was no liquid. Had they failed? The temperature probes read a staggering 4.5 Kelvin, but the helium was still a gas. Then, just as doubt was setting in, someone noticed something. Inside the innermost chamber, a faint, almost invisible line appeared against the glass wall. It was a liquid surface. Onnes himself came over to look. They had done it. They had liquefied helium. At 4.2 Kelvin, a mere whisper from absolute zero, the last gas had been conquered. Kamerlingh Onnes had won the final battle of the liquefaction wars. He hadn't just set a new record, he had opened the door to a whole new realm of physics. And what he would find there was stranger than anyone could have possibly imagined. The strange new world near zero. With liquid helium basically on tap, Heike Kamerlingh Onnes held the key to an unexplored universe. The race to reach the cold was over. The race to understand it was just beginning. In 1911, just 3 years after liquefying helium, he and a student made a discovery that would completely shake up physics. On paper, the experiment was simple. They were measuring the electrical resistance of a thin wire of solid mercury as it was cooled down. The going theory was that a metal's resistance should drop as it gets colder, since the jiggling atoms that get in the way of electrons calm down. Lord Kelvin thought resistance would eventually become infinite as electrons froze to their atoms. Others figured it would just level off. As the team cooled the mercury, things went as expected. The resistance dropped steadily. But then, as the temperature approached 4.2 Kelvin, something astonishing happened. The resistance didn't level off. It didn't climb. It just vanished. One moment it was there, and the next it dropped to a value so small their instruments couldn't measure it. They thought it had to be a short circuit. It seemed impossible. They checked everything, ran the experiment again, and got the same result. Below a critical temperature of 4.2 K, Mercury's electrical resistance was gone. Onnes had discovered superconductivity. This wasn't some minor tweak, it was a whole new state of matter. In this superconducting state, an electrical current started in a loop of wire would flow forever, without a power source, as long as it was kept cold. In a famous demonstration years later, a superconducting current was started in a lead ring in Leiden and then flown to London. The current was still flowing, undiminished, in a different country. The implications were staggering. Electricity without resistance meant electricity without loss. It was the first clue that the world near absolute zero doesn't play by the normal rules. It was a quantum world, and the weirdness was just getting started. As physicists dug deeper, they found that helium itself was even stranger. Liquid helium, it turns out, isn't just one liquid. Above 2.17 Kelvin, it's a normal, if very cold, liquid. But cool it below that specific temperature, the lambda point, and it transforms into a second state called helium-2. And helium-2 is no ordinary liquid. It's a superfluid. A superfluid is a liquid that flows with zero viscosity, zero friction. Imagine stirring your coffee and having it swirl forever. That's a superfluid. If you put it in a container, it will spontaneously climb the walls and flow over the top, seemingly defying gravity. It can seep through microscopic cracks that are totally sealed to normal liquids. It conducts heat so perfectly, thousands of times better than copper, that it can't even boil. Instead, the heat is whisked away so fast that the entire volume just evaporates at once. Watching a superfluid is like watching a magic trick. At these ultra-low temperatures, the quantum weirdness usually confined to the subatomic world was bubbling up into our world. The individual helium atoms were losing their identities, overlapping and moving as one single, coherent quantum state. These discoveries weren't just cold curiosities, they were windows into the fundamental nature of reality. Cooling things down wasn't just about slowing atoms. It was about revealing a hidden layer of physics normally masked by the thermal noise of our warm world. The quest had led scientists into a strange new wonderland, but it was also leading them straight into an unclimbable wall. The journey to absolute zero revealed that the universe is far stranger at its limits than we ever guessed. And these discoveries are the foundation for technologies that are shaping our future, from MRI machines to quantum computers. If you're enjoying this trip into mind-bending physics, do us a favor and hit that like button and subscribe to the channel. It really helps us keep making deep dives just like this one. Now, let's get back to the impossible quest, and the paradox that lies at its heart. The quantum paradox. Why stillness is an illusion. So, by the early 20th century, scientists were within a few degrees of absolute zero. They'd discovered bizarre new states of matter. The finish line was in sight, 0 Kelvin. The point of perfect stillness. It seemed so close. But the closer they got, the harder nature pushed back. Every new step required exponentially more effort for a smaller and smaller return. Getting from 4 Kelvin to 1 Kelvin was hard. Getting from 1 Kelvin to 0.1 Kelvin was monstrously difficult. And going further felt, well, impossible. This wasn't just an engineering problem. It was a new law of the universe that physicists were just starting to wrap their heads around. The third law of thermodynamics. The first two laws are about energy and disorder. The first law: you can't create or destroy energy. The second law: the total disorder, or entropy, of the universe always increases. Heat flows from hot to cold. The third law basically says that the entropy of a perfect crystal at absolute zero is zero. It's the ultimate state of order. But this law comes with a profoundly frustrating consequence. It is impossible to reach absolute zero. Think of it like this. You're trying to get to a finish line, but with each step, you can only cover half the remaining distance. You run halfway, then you run half of what's left. then half of that remainder, and so on. You will get infinitely, tantalizingly close. You can get within a millimeter, a nanometer, a picometer, but you will never, ever actually cross the line. Each step only takes you a fraction of the way there. Reaching absolute zero is exactly like that. Every cooling process we invent is just another step that takes us a fraction of the way closer, but the destination, 0K, remains infinitely far away. The third law of thermodynamics put up a giant, invisible wall right before the finish line. Absolute zero is an unreachable destination. But here's the bigger twist. Even if you could magically get there, the dream of perfect, utter stillness is a lie. And the reason for this is the most famous rule in all of quantum mechanics, the Heisenberg uncertainty principle. Werner Heisenberg discovered that you can't know certain pairs of a particle's properties at the same time. The classic example is position and momentum. The more precisely you measure a particle's position, the less you know about its momentum, and vice versa. This isn't because our tools are clumsy, it's a fundamental fuzziness baked into reality itself. So, let's apply this to an atom at our imaginary absolute zero. If it were perfectly still, its momentum would be exactly zero. But the uncertainty principle says if you know the momentum perfectly, then you must have infinite uncertainty about its position. The atom could be literally anywhere in the universe. That clearly doesn't happen. To resolve the paradox, the atom can never be perfectly still. It must always have a tiny, irreducible minimum amount of energy. A quantum tremor. This is called the *0-point energy. Think of a guitar string. You can think it eventually stops vibrating and becomes perfectly still. But in the quantum world, it never does. Even in its lowest possible energy state, it's still humming with a faint, unquenchable vibration. This is its 0-point energy. It's the energy something has even when all the heat has been removed. It's the energy of just existing. So, even at absolute zero, a temperature defined by the absence of heat, atoms are not stationary. They are constantly fluctuating, vibrating with this baseline quantum energy. Perfect stillness is a cosmic illusion. The universe, at its core, refuses to stand still. This discovery transformed the quest. The goal was no longer to achieve perfect rest, which was now impossible for two profound reasons. Instead, the race had just become infinitely more interesting. The modern race, pushing the limits. Liquefying helium got us to within 4 degrees of absolute zero. But to get into the truly bizarre microkelvin, nanokelvin, and even picokelvin regimes, scientists needed entirely new weapons. The old brute force methods had hit their limit. The modern race to the bottom isn't fought with giant machines, but with the elegant tools of quantum physics, lasers and magnets. One of the coolest techniques is called laser cooling. And yes, that sounds completely backward. How do you cool something with a laser, which is a beam of energy? The secret is momentum. Photons, the particles of light, carry a tiny kick. Imagine an atom moving toward a laser beam. If you tune the laser's frequency to be just a tiny bit below what the atom naturally absorbs, something neat happens because of the Doppler effect. Since the atom is moving towards the light, it sees the frequency as slightly higher, the perfect frequency to absorb a photon. So, the atom absorbs a photon coming straight at it and gets a kick that slows it down. A moment later, it spits the photon back out, but in a totally random direction. Over thousands of these cycles, the kicks from the laser beam act like a powerful brake, while the random kicks from re-emission average out to zero. By setting up 6 lasers in opposing pairs, scientists can create optical molasses. Any atom that tries to move in any direction gets pushed back to the center. The atoms are trapped and slowed to a crawl, and the temperature of the cloud plummets to millionths of a degree above absolute zero. To get even colder, they use another trick: evaporative cooling. It's the same reason you feel cold when you sweat. The fastest, most energetic water molecules escape, leaving the cooler ones behind. In the lab, atoms are held in an invisible, magnetic bowl. Scientists then slowly lower the lip of this bowl, letting the hottest, most energetic atoms fly out. With the hotheads gone, the average energy and temperature of the atoms left behind drops. By carefully shaving away the energetic atoms, they can drive the temperature down into the nanokelvin range, billionths of a degree above absolute zero. Using these methods, scientists have gotten mind-bogglingly close to the limit. In research published in 2021, a team of German researchers announced they had achieved the coldest temperature ever recorded. They took a cloud of rubidium atoms and formed a Bose-Einstein condensate, then dropped it down a 120-meter-tall tower in Bremen, Germany. In the microgravity of the freefall, they used a special magnetic lens to slow the expansion of the atom cloud, reducing its internal motion to almost nothing. The result was a staggering 38 picokelvins. That's 38 trillionths of a degree above absolute zero. To put that in perspective, the vast emptiness of space is about 2.7 Kelvin because of the afterglow from the Big Bang. The coldest known natural place is the Boomerang Nebula, 5,000 light-years away, which is a frigid 1 Kelvin. So, the coldest thing in nature is 1 Kelvin. The lab record is 0.000000000038 Kelvin. This means that, for a few years now, the coldest spot in the entire universe has been inside a laboratory in Germany. We've created a state of matter millions of times colder than anything that exists naturally, and in this impossibly cold and quiet environment, the true promise of this quest is finally being realized. Why we chase the impossible, the technological payoff. The chase for a temperature we can never reach might seem a little abstract. But this impossible quest has produced some of the most profound discoveries and revolutionary technologies of our time. The quantum phenomena that emerge from the cold aren't just curiosities, they're tools. The first and most obvious one is superconductivity. That disappearing electrical resistance on us found in 1911 now powers our most advanced instruments. The most powerful magnets on Earth are superconducting. In an MRI machine, a loop of superconducting wire carries a massive current with zero energy loss, creating the intense magnetic fields needed to see inside the human body. The same tech is at the heart of particle accelerators like the Large Hadron Collider, where giant superconducting magnets steer particles at nearly the speed of light, all while being bathed in liquid helium to stay at just 1.9 Kelvin, colder than deep space. But the truly futuristic tech comes from the even colder temperatures. When you cool certain atoms into the nanokelvin range, they collapse into a new state of matter predicted by Albert Einstein and Satyendra Nath Bose back in the 1920s. A Bose-Einstein condensate or BEC. In a BEC, the quantum waves of thousands of individual atoms overlap and lose their separate identities. They begin to behave as a single, massive quantum object, a superatom, governed by one collective wave function. The quantum weirdness that's normally hidden from us becomes visible on a macroscopic scale. This was finally achieved in 1995, earning a Nobel Prize. Scientists had created the fifth state of matter. And this superatom can do incredible things, like create an atom laser. Instead of a beam of light, it emits a coherent beam of matter itself, which could revolutionize things like etching impossibly small computer chips. BECs are also insanely sensitive. The slightest change in gravity or rotation can disturb their delicate quantum state in a measurable way. This makes them perfect for ultra-precise sensors. Scientists are building atomic clocks so accurate they wouldn't lose a second in the entire age of the universe. These are essential for GPS and deep space navigation. Cold atom sensors can detect tiny gravitational shifts, allowing us to map underground water or even predict volcanic eruptions. But maybe the most transformative application is in quantum computing. A normal computer uses bits, zeros and ones. A quantum computer uses qubits. A qubit can be a 0, a 1, or, thanks to quantum mechanics, both at the same time. This gives them the power to solve problems that are impossible for even the fastest supercomputers. The biggest challenge is protecting the qubits from the outside world. Any stray heat or vibration can destroy their fragile quantum state. This is where absolute zero comes in. The ultra-cold, ultra-quiet environment near 0K is the perfect sanctuary for qubits. The road to the quantum revolution is paved with liquid helium. The mind-bending twist: negative Kelvin temperatures. Okay, so we've established that absolute zero is the coldest possible temperature. Nothing can be colder. The laws of physics forbid it. This is the bedrock of how we understand temperature. So, what if I told you that scientists have created temperatures of -1 nanokelvin? That's right, a negative temperature on the absolute Kelvin scale. This sounds like it should be impossible. It sounds colder than cold. But the reality is much, much stranger. A negative Kelvin temperature is not colder than absolute zero. It is, in fact, infinitely hotter than any positive temperature. To wrap your head around this, we have to rethink what temperature actually is. Statistically, it's about how energy is distributed among particles. In any normal system, there are always more particles in lower energy states than in higher ones. As you add heat, particles move to higher energy states, but the pyramid structure remains: more at the bottom, fewer at the top. This is a normal, positive temperature. But what if you had a special system, one with a maximum possible energy level? Imagine a set of quantum spins in a magnetic field. Each can only be in a low energy state or a high energy state. That's it. At positive temperatures, most spins are in the low energy state. But what if you used some clever tricks to force more than half of them into the high energy state? This is a population inversion. It's the principle behind how lasers work. You now have an upside-down pyramid, with more particles at the top than the bottom. If you put this system next to any object at a positive temperature, even a trillion degrees, heat would flow from your negative temperature system to the positive temperature one. And since heat always flows from hotter to colder, your negative Kelvin system is, by definition, hotter. So the temperature scale isn't a simple line. It's more like a circle. You start at absolute zero, minimum energy. You add energy, and the temperature goes up toward positive infinity. At positive infinity, you have a random distribution of energy. If you can keep adding energy to create a population inversion, you jump across to negative infinity. From there, adding even more energy warms it up toward zero from the negative side. A negative Kelvin temperature is a state that is, paradoxically, hotter than infinity. This doesn't break the third law, which is about reaching the zero energy ground state. Negative temperatures are bizarre, high energy states that only exist in special quantum systems. But they're a stunning reminder that our everyday intuition completely breaks down at the extremes. The quest for the ultimate cold led us to discover a realm that is, by all definitions, the ultimate hot. Conclusion: the quest for absolute zero started with a simple idea. If you get things cold enough, everything will just stop. It was a race to an imagined point of perfect silence. But what a century of relentless chasing has taught us is that the universe is far too clever and far too strange for such a simple ending. The journey took us through the fiery rivalries of the liquefaction wars, where brute force brought us to the edge of the quantum world. There, we found not silence, but a symphony of strange phenomena, matter with perfect efficiency and liquids that defy gravity. And then, just as the goal seemed within reach, physics put up two giant stop signs. The third law of thermodynamics showed us that absolute zero is an infinite journey we can never complete. And the Heisenberg uncertainty principle revealed that even if we got there, the prize we wanted, perfect stillness, was a cosmic illusion, forbidden by a fundamental quantum jitter that can never be silenced. So, the race changed. It became a quest for deeper understanding. Armed with lasers and magnetic traps, we've pushed trillions of times colder than anything in nature. And from these depths, we have pulled the future, MRI machines, ultra-precise sensors, and the cradles for the coming quantum computing revolution. The impossible quest for absolute zero is a story about science itself. We chase a simple question and find answers to questions we didn't even know how to ask. We set out to find the point where all motion ceases, and instead, we found the fundamental motion that can never cease. We sought perfect order, and found a paradox that turned our definition of hot and cold inside out. So if true stillness is impossible, and the universe hums with a permanent quantum energy, what does that really say about the nature of reality? Is the cosmos destined to be forever in motion? At its very core, can the universe simply not be quiet? The quest continues. If you want to explore more mind-bending physics and the profound questions that drive science forward, be sure to subscribe and click the bell icon so you don't miss our next video. And check out our other explorations into the cosmos right here. The ghost energy hiding in empty space. We have long thought of empty space as an absence. A perfect void, where nothing happens and nothing exists. But this understanding, like many of our intuitions about the world, is incomplete. What if this apparent nothingness is in fact a sea of quiet, persistent energy? A fundamental tremor woven into the fabric of reality itself. This is the story of the energy of the vacuum, a force so fundamental it shapes the universe on both the smallest and largest of scales. This is the secret of zero-point energy. What we are about to explore is a concept that sits outside our everyday experience. It is a journey from the coldest, quietest corners of the cosmos to the heart of quantum mechanics, and it begins with a simple question. What does it mean for something to be truly still? We believe we know the answer. Stillness is the absence of motion, the absence of energy. The universe, it turns out, operates by a different rule. And that difference changes our understanding of everything. Imagine a place in the deepest void of intergalactic space, far from any star. The temperature there can approach as low as it can possibly get, absolute zero. At this temperature, all classical motion is supposed to cease. Atoms should stop vibrating. Everything should be frozen in a state of perfect rest. And yet, it is not. Even in the most profound cold and emptiness, reality is alive with an unavoidable jitter. This is not an anomaly, but a fundamental law of existence. Even when a system reaches its absolute lowest energy state, it can never be perfectly still. Today, we will explore this quantum restlessness. We will look at the core principle that forbids true stillness in our universe, and then examine the mind-bending proof from real-world experiments. By the end of this journey, the idea of stillness will reveal itself as an illusion, and the nothing of empty space will be understood as one of the most powerful and mysterious somethings we have ever encountered. Our intuitive sense of the world is built on classical physics. To stop a rolling ball, you remove its energy through friction. If you could remove all the energy from any system, it would become perfectly motionless. Its position would be fixed, its motion zero. This is the world Isaac Newton described, and for our daily lives, it works perfectly. But just over a century ago, our perception of reality was altered. We discovered that at the smallest scales, the rules change. The universe, at its most fundamental level, is quantum. And in the quantum world, the idea of perfect stillness is not permitted. To understand why, it helps to picture a single guitar string. When plucked, it vibrates, creating a musical note. The string can vibrate at a fundamental frequency and at various overtones, each carrying energy. In the classical world, to silence the strain, you would remove all its energy, cooling it until it became a perfectly flat, motionless line. It would have zero energy and zero motion. A quantum system, however, behaves differently. In the quantum world, every particle and every point in space can be thought of as a quantum harmonic oscillator, a microscopic, invisible spring that is constantly in motion. When you try to cool one of these quantum oscillators to its lowest possible energy state, what physicists call the ground state, it does not go silent. It retains a tiny, irreducible amount of energy. It continues to hum with a baseline level of motion. This minimum, non-zero energy is the zero-point energy. The reason for this lies in one of the most foundational principles of physics, Heisenberg's uncertainty principle. Werner Heisenberg discovered a fundamental limit to what we can know about a particle. The principle states that you cannot simultaneously know both its precise position and its precise momentum. The more accurately one is known, the less accurately the other can be. This is not a limitation of our instruments, it is a property of the universe itself. Let us return to our motionless guitar string. If it were perfectly still, its position would be known with absolute certainty, a flat line. And its momentum would also be known with absolute certainty, zero. We would know both its position and its momentum perfectly. And this is something the universe does not permit. Heisenberg's uncertainty principle forbids such a state. To satisfy this cosmic law, a compromise is reached. A particle settles into its lowest possible energy state, the ground state, which represents a trade-off. It has a fairly well-defined position, but its momentum fluctuates around zero. Its position is not a perfect point but is smeared out in a small cloud of probability. This inherent, unavoidable jitter is the source of zero-point energy. This quantum restlessness is not caused by the uncertainty principle. It is the other way around. The fact that all quantum systems possess this non-zero ground state energy is what leads to the uncertainty in our measurements. The universe is fundamentally restless at its core, and that restlessness manifests as a limit on what we can ever know about it. So, a fundamental jitter exists for any single particle. But what does this have to do with the vacuum of empty space? Here, we must expand our thinking from a single particle to the fabric of space itself. In modern physics, space is not an empty stage. It is filled with dynamic substances called quantum fields. There is a field for every fundamental particle, an electron field, a photon field, and so on. These fields permeate all of existence. What we see as a particle, like an electron, is a localized vibration in its corresponding field, a small knot of energy. A perfect vacuum, then, is a space emptied of all particles. It is just the fields, resting in their ground state. And just like a single quantum oscillator, these fields can never be perfectly still. Every point in every quantum field is a quantum harmonic oscillator, and each possesses a non-zero ground state energy. The collective, universe-spanning jitter of all these fields is the zero-point energy of the vacuum. This leads to one of the most unusual ideas in science, virtual particles. The uncertainty principle also relates energy and time. For very short periods, the law of conservation of energy can be briefly suspended, allowing for tiny fluctuations. For an incredibly brief moment, a bit of energy can be borrowed from the vacuum to create a particle-antiparticle pair, such as an electron and a positron. This loan from the universe must be repaid almost instantly. The two particles find each other and annihilate, disappearing back into the vacuum and repaying the energy they borrowed. These are called virtual particles. They are the physical manifestation of the vacuum's zero-point fluctuations. They are the jitter made tangible. Empty space, therefore, is not empty. It is a quiet, constant activity of virtual particles, being born from nothing and returning to nothing. The net energy of this process averages to zero over time, but the activity is real. The hum is real. and its presence has measurable effects on the universe. This may sound like a mathematical abstraction. For a long time, the energy was present in the equations, but the challenge was to find physical proof. Then, in 1948, the Dutch physicist Hendrik Casimir found its signature while working on an unrelated industrial problem. Casimir was investigating forces between particles in colloidal fluids for Phillips research labs. The existing theories did not match the data. After a conversation with the physicist Niels Bohr, who suggested the strange forces might relate to vacuum energy, Casimir did the math. He theorized that two smooth, uncharged metal plates placed incredibly close together in a vacuum would experience a force pushing them together. The logic behind this was subtle and brilliant. In the empty space outside the two plates, virtual photons of all possible wavelengths can exist. But the space between the plates acts as a resonant cavity. It can only host virtual photons whose wavelengths fit neatly into that gap, excluding longer ones. This creates an imbalance. A wider range of virtual particles pushes on the outside of the plates, while a more limited set pushes from the inside. The pressure from the outside is therefore greater than the pressure from the inside, and the plates are pushed together. A useful way to visualize this is to imagine two ships in a stormy ocean. Far apart, they are pushed by waves from all sides. But if they move very close, the water between them calms, as the long ocean swells cannot fit in the narrow gap. The ships are then pressed together by the more powerful waves on their outer hulls. This is an analogy for what Casimir predicted. The ships are the plates, and the waves are the virtual particles. This prediction, the Casimir effect, was a direct consequence of zero-point energy, the idea that nothing could exert a real, mechanical force. For decades, the force was too small to be measured, easily lost among other forces. But technology improved. In 1996, physicist Steve Lamoureux devised an experiment of sufficient precision. Using a sensitive torsion pendulum, he measured the attraction between a tiny gold-coated sphere and a plate. After accounting for all other possible forces, a small, residual attractive force remained. Its strength matched Casimir's prediction with remarkable accuracy. The measurement confirmed it. The vacuum could push. The Casimir effect is just one piece of evidence. Another is the Lamb shift. The energy levels of electrons in a hydrogen atom are slightly shifted from where simple theory predicts they should be. This occurs because the electron is constantly being jiggled by the virtual particles of the vacuum, and this jostling alters its energy. There is also spontaneous emission. An excited atom emits a photon not just on its own, but because the vacuum fluctuations nudge it, stimulating it to decay. These are not theories but lab-verified facts. They are receipts from the universe, proving that empty space is a dynamic and powerful medium whose energy shapes the world we see. So, the vacuum has energy. It can push plates and jiggle electrons. But this is where the story takes a profound turn. Physicists wanted to calculate the total energy density of the vacuum. When they summed up the zero-point energy from all the known quantum fields in a cubic meter of space, the number they got was shocking. The theoretical energy density of the vacuum is around 10 to the power of 113 joules per cubic meter. This value is so large it is difficult to comprehend. The energy contained in all the matter of the entire observable universe is trillions of times smaller than the theoretical energy locked in a single cubic meter of empty space. This is the phantom's true scale. According to our most tested theory of reality, we are living in an ocean of energy so dense it defies intuition. This leads to an immediate problem. Energy on this scale should have a gravitational effect so powerful it would have ripped the universe apart before stars or galaxies could ever form. We would not be here. And yet, we are. When astronomers measure the expansion of the universe, they do find it is accelerating, pushed apart by a force they call dark energy. This dark energy acts like a form of vacuum energy. But when they measure its strength, they find it is incredibly weak, about 10 to the power of minus 9 joules per cubic meter. We have the theoretical prediction, 10 to the power of 113. And we have the observed value, 10 to the power of minus 9. The difference is a factor of 1 followed by roughly 122 zeros. It is perhaps the single greatest disparity between theory and observation in the history of science, known as the cosmological constant problem, or the vacuum catastrophe. What explains this discrepancy? One idea is that there is an undiscovered symmetry in nature. Quantum fields for some particles contribute positive energy, while others contribute negative energy. Perhaps these contributions cancel each other out, with a precision of 122 decimal places. Another possibility is that our understanding of gravity is incomplete. A more philosophical proposal is the anthropic principle, which suggests we exist in a multiverse. Most universes have a huge vacuum energy and are sterile. We simply find ourselves in one of the rare universes where, by chance, the value is small enough to allow life to exist. We do not know the answer. The cosmological constant problem is a deep mystery, telling us that a profound connection between the quantum world and the cosmos remains just beyond our understanding. The sheer scale of this energy has captured the imagination of many. If even a fraction of it could be accessed, it would represent a source of limitless, clean power. This is the promise of zero-point energy often seen in speculation and science fiction. Here, however, we must tread carefully and separate science from hope. Harnessing this energy is not a simple matter of extraction. The ground state is, by definition, the lowest possible energy state. You cannot take energy from it, as there is no lower state for it to fall into, just as water cannot flow out of the bottom of a valley. The Casimir effect does not extract net energy. It only releases a tiny amount by changing the system's configuration. To reset the system by pulling the plates apart requires more energy than was gained. Any technology to harness vacuum energy would need to manipulate the ground state itself, a challenge far beyond anything we are capable of today. The allure of free energy has attracted claims that lack credible evidence and often defy fundamental laws of thermodynamics. Real scientific progress is happening in nanotechnology, where scientists are learning to control the Casimir force to prevent tiny machine parts from sticking together. This is a story of control, not extraction. So, while the dream of a ZPE-powered future is a powerful one, we must remain grounded in the science. The vacuum is not yet ready to give up its power. But the pursuit of this mystery pushes the boundaries of our knowledge, and in science, the pursuit itself is often where the most important discoveries are made. Our journey began with the idea of empty space, which we have found to be an illusion. We discovered that nothing can ever be truly still, and that space is filled with a restless hum of zero-point energy. We saw how this energy is real, leaving its signature in the form of the Casimir effect, which proves that nothing is powerful enough to move something. Then, we confronted the ghost's true scale, and the profound mystery of the vacuum catastrophe, the gap in our knowledge that connects the very small to the very large. And finally, we looked to the future, to the cautious but compelling search to understand this power. The story of zero-point energy shows how science works. It begins with a fundamental question, leads to predictions that challenge our view of the world, and demands rigorous proof. It reveals that the universe is far more complex and alive than we imagined. The space we thought was a silent emptiness is, in fact, the most energetic stage of all. The universe abhors a true standstill. And as we continue to probe the mysteries of the vacuum, we are reminded that some of the deepest secrets are hidden not in distant galaxies, but in the apparent nothingness all around us, waiting patiently for understanding to catch up. If you enjoyed this calm exploration into the fundamental nature of reality, consider subscribing to the channel. And let me know in the comments, what cosmic puzzle do you want to explore next? The force in nothingness that breaks physics. Imagine two perfectly smooth metal plates, just floating in a perfect vacuum. There's nothing between them, nothing around them, no gravity, no air, not a single force you could name. So what should happen? Well, logic says, nothing. They should just hang there, forever, untouched and unmoved in the silent, empty void. That's the world we think we know, right? A world governed by predictable rules where things only happen when something makes them happen. But in the real world, something impossible occurs. The plates start moving. They're pushed together by a mysterious force that seems to come from absolutely nowhere. This isn't science fiction, and it's no trick. It's a real experiment, and the secret it unlocks will forever change how you see nothing. It reveals a hidden, violent reality simmering just beneath the surface of everything, proving that even the most perfect emptiness is a raging storm of energy powerful enough to rewrite the rules of physics. Stick around, and I'll show you how nothing might just be the most powerful something asterisk in the entire universe. The old world, a universe of quiet emptiness. To really get your head around how wild this idea is, we need to take a quick step back. Back to a simpler time, the age of classical physics, the world of Isaac Newton and James Clerk Maxwell. In their universe, everything was like a grand cosmic stage. The actors were planets, stars, and atoms. And the stage itself? That was space. And for the most part, space was considered to be, well, empty. The idea of a true void, a place with no matter at all, has fascinated and bothered people for thousands of years. The ancient Greek philosopher Aristotle famously said that nature abhors a vacuum, basically arguing that true emptiness was impossible. It just felt wrong. How could nothing even exist? But as science got better, our thinking changed. We discovered air pressure and realized that an empty jar is actually swarming with billions of air molecules. With the invention of the vacuum pump in the 17th century, we got better and better at creating a true void. The scientific view began to flip. Space wasn't a substance, it was just a backdrop. An absolute, silent, featureless arena where the drama of the universe played out. In this classical world, a vacuum was the very definition of passive. It was zero. It had no properties, no energy, no substance. It was just the absence of everything else. If you put two objects in it, with no gravity or other forces, they were expected to stay perfectly still, forever. A force needed a source. A planet, a charge, a magnet, a gust of wind. No source, no force. This was a bedrock assumption of physics for hundreds of years. The universe was made of things, and the space between those things was nothing. And nothing, by its very definition, can't do anything. This clean, orderly picture worked beautifully. It let us chart the paths of planets, understand electricity, and build the entire industrial revolution. It was a universe that made sense. But as the 20th century dawned, a few intellectual earthquakes started to rumble, and the peaceful emptiness of the void was about to be shattered forever. The new physics, quantum mechanics, was getting ready to show that the quiet, empty stage was actually the most chaotic actor of all. The glitch in reality. The story of how we found this force from nothing doesn't start in some grand university hall. It starts in the 1940s, in the industrial research labs of the electronics giant Philips. A Dutch physicist named Hendrik Casimir was there, and he wasn't trying to rewrite cosmology. He was trying to solve a very practical problem involving things like mayonnaise and paint. These are called colloidal solutions, basically, microscopic particles suspended in a liquid. Phillips was interested in these goopy materials but was running into a strange problem. The tiny particles weren't behaving quite like the theories of the day predicted. There's a known force called the van der Waals force, which is a kind of weak, residual stickiness that exists between all neutral atoms and molecules. It was essential for understanding the colloids at Phillips. But one of Casimir's colleagues, Theo Overbeek, noticed that the existing theory seemed to break down for larger particles at greater distances. The math just didn't match what they were seeing. So, Overbeek asked Casimir, a top-tier theoretical physicist, to take a look. Working with another physicist, Dirk Polder, Casimir dug into the math. They realized the original theory had a tiny flaw. It assumed the electromagnetic pull between two molecules happened instantly. But Einstein's theory of relativity says nothing travels faster than light. They added this retardation, the tiny delay for the force to travel, into their math. And it worked. Their new theory, now called the Casimir-Polder force, perfectly described the interaction. But this is where the story pivots from the practical to the profound. Casimir wasn't totally satisfied. He felt there had to be a cleaner, more fundamental way to explain this. He later remembered talking with the legendary Niels Bohr, one of the founders of quantum mechanics. As Casimir was explaining his complicated math, Bohr just mumbled something like, "It must have something to do with zero-point energy." Zero-point energy. This was a seriously weird idea straight out of the bizarre rulebook of quantum mechanics. We'll get into the weeds with it later, but for now, think of it this way. Quantum mechanics says nothing can ever be perfectly still or have zero energy. There's always a minimum amount of jittering that can never be stopped. This leftover energy, flapping around even in a perfect vacuum at absolute zero, is called the zero-point energy. Bohr's comment was a light bulb moment. Casimir started to wonder. What if this force isn't really about the two molecules at all, but about how they interact with the zero-point energy of the vacuum around them? He figured if that was true, the effect should be way simpler if you just used two perfectly conducting metal plates instead of complicated molecules. So he imagined it. Two perfectly smooth, uncharged metal plates in a perfect vacuum. In the old world, nothing should happen. But Casimir, using these strange new quantum ideas, predicted something extraordinary. He predicted the two plates would be drawn to each other by a force coming purely from the vacuum itself. A force from nothing. An impossible force. He published his prediction in 1948. The idea was so strange, so counterintuitive, that for decades it was just a theoretical curiosity, a glitch in reality, waiting for someone to prove it was real. The first bridge, making sense of the impossible. Okay, a force from nothing. How do we even begin to think about that? When an idea is this strange, the best thing to do is find an analogy to act as a bridge from our world to the quantum world. The most famous one is the ships at sea analogy. Picture two big ships floating on the ocean. Out on the open sea, you have waves of all sizes, long, rolling swells and short, choppy ones. The ocean is a chaotic mix of all of them. Now, what happens when those two ships drift very close together, parallel to each other? Something interesting happens in the narrow channel of water between the ships. That space is now restricted. Only waves that can fit into that gap can really form. The long, rolling swells are just too big to exist in that tiny space. So, the only waves you find between the ships are the short, choppy ones. Meanwhile, on the outside of the ships, the open ocean is still going crazy. Waves of all sizes are still crashing against the outer hulls. So now you've got a situation where there are more waves, and therefore more energy and pressure, pushing on the asterisk outside of the ships than there are on the inside. The result? The ships are pushed together. It isn't some mysterious force pulling them. It's simply the pressure from the outside world being greater than the pressure from the inside. While this specific effect isn't something sailors observe, it serves as a powerful illustration. Now, let's swap the ocean for the vacuum of space, and the water waves for the vacuum fluctuations, or zero-point energy, that Niels Bohr mentioned. According to quantum mechanics, empty space isn't empty. It's filled with a sea of roiling, virtual, electromagnetic waves of every possible wavelength, popping in and out of existence in a constant, invisible storm. When you put our two metal plates in this vacuum, they act just like the ships. The space between them is restricted. Only virtual waves that fit neatly into the gap can exist in there. The longer wavelength fluctuations are shut out. But on the asterisk outside of the plates, the vacuum is still a chaotic soup of fluctuations of all possible wavelengths. There are no restrictions. Just like the ships, you get a pressure imbalance. The relentless storm on the outside is stronger than the calmer, restricted storm on the inside. This greater external pressure pushes the plates together. This is the Casimir effect. It's a force born not from something between the plates, but from the exclusion of something that is everywhere else. Another way to think of it is like acoustics. In a huge, open field, you can hear all kinds of sounds. Walk into a small room, and the walls change everything. The room has resonant frequencies, notes that sound strong because their wavelengths fit perfectly inside, but it also dampens or cancels out other sounds that don't fit. The acoustic environment is different inside versus outside. The Casimir effect is the quantum vacuum version of this. The plates create a room in the vacuum, and the properties of this room for virtual waves are different from the wide open vacuum. This creates an energy difference, which we feel as a force. The energy density of the vacuum between the plates is actually lower than the vacuum outside. Nature always wants to find the lowest energy state, so it tries to close the gap, pushing the plates together to shrink this low energy zone. It's critical to get this. The force is attractive because the nothing between the plates is literally less than nothing. It's a patch of vacuum with negative energy density compared to the vacuum around it. This was one of the first stunning predictions in physics of a real, negative energy state. These analogies aren't perfect, but they give us a powerful way to think about it. They show how just putting up boundaries can change the fabric of the vacuum itself, turning empty space into a source of real force. The prediction was made. The only question left was, could this impossibly faint force ever actually be measured? From theory to fact, touching the void. For nearly 50 years, Hendrik Casimir's prediction was just a mind-bending piece of theory living on paper. The reason was simple. The force he described was predicted to be incredibly, almost laughably, weak. Think about the forces in our daily lives. Gravity pins us to the earth. Electromagnetism powers our world. These are obvious, powerful forces. The Casimir force, in comparison, is a whisper. It only becomes noticeable when the distance between the two plates gets absurdly small, on the order of micrometers, millionths of a meter, or nanometers, billionths of a meter. At a separation of just 10 nanometers, the pressure, under idealized conditions, can be compared to the atmosphere around us, but it drops off incredibly fast as the distance increases. Measuring a force that tiny is a monumental challenge. Dozens of other things could get in the way. Stray electric charges, gravity, and making sure the plates are perfectly smooth and, worst of all, perfectly parallel. Getting two surfaces perfectly parallel on a microscopic scale was a huge roadblock. Early attempts were made. In 1958, Marcus Sparney, also at Philips, tried an experiment. His results were inconclusive. He admitted an error margin of 100%, but wrote that his findings were not in contradiction with the Casimir theory. It was a heroic attempt, but it wasn't proof. For decades, the force from nothing remained a ghost. Then, in 1997, everything changed. At Los Alamos National Laboratory, a physicist named Steve Lamoureux came up with a brilliant new experimental design. He completely sidestepped the parallelism problem. Instead of two flat plates, he used one flat plate and one plate that was part of a very large sphere. This clever setup made the geometry much easier to handle. The distance between them was just the distance from the flat plate to the closest point on the sphere. Lamoureux attached the spherical plate to a hypersensitive torsion pendulum. By moving the flat plate closer to the sphere, any tiny attractive force between them would cause the pendulum to twist by a measurable amount. The experiment was unbelievably delicate, performed in a high vacuum to get rid of air currents and shielded from heat and vibrations. After all that painstaking work, Lamoureux succeeded. He measured a tiny attractive force that grew stronger as the plates moved closer, at distances on the micrometer scale. His measurements were a landmark confirmation of Casimir's theory, matching the predictions well within the experiment's level of uncertainty. After 49 long years, the ghost was caught. The force from nothingness was real. This experiment was a huge moment in physics. It was the first direct, quantitative measurement of the Casimir effect. It proved that the bizarre predictions of quantum mechanics weren't just math, they described the real world. The vacuum was not empty. It had a real energy that could push and pull on things. Since Lamoureux's breakthrough, other experiments have confirmed and refined the measurement, nailing it down with incredible accuracy. The confirmation of the Casimir effect was more than just checking a box on an old theory. It was a profound statement about reality itself. It proved that the universe is a quantum place, all the way down. The classical idea of a peaceful, empty void was officially dead. The stage wasn't empty, it was alive with a storm of quantum energy, and we had finally learned how to feel its push. Alright, let's hit pause and recap, because we've covered a lot of ground. We started with a simple puzzle: two metal plates in a vacuum getting pushed together by nothing. We learned how this wild idea came from a very practical problem with paint and mayonnaise at Phillips Labs, which led Hendrik Casimir to predict this force. We used the analogy of ships at sea to get a feel for why it happens, how the plates block certain virtual waves, creating a pressure imbalance between the chaotic energy outside and the calmer sea inside. And finally, we saw how in 1997, Steve Lamoureux proved this wasn't just a quirky theory, but a real, measurable force of nature. So, we've established that the force is real. But that just leads to a much deeper question. What is this storm in the vacuum? What are these virtual particles? To answer that, we have to go to the very heart of modern physics, to a theory often called the most beautiful and powerful ever conceived, quantum field theory. The next part of our journey gets even weirder, as we try to understand the true nature of particles, forces, and the vacuum itself. If you're finding this as fascinating as I am, make sure you're subscribed and have notifications turned on, because you really won't want to miss what's coming. The deeper reality, the living vacuum. So far, we've used helpful analogies like ships and soundproof rooms, talking about virtual waves. But those are just stepping stones. To really understand the Casimir effect, we have to look at the reality underneath it all. That reality is described by quantum field theory, or QFT. And let's be clear, QFT is one of the most brain-bending subjects in all of science. Even physicists who work with it every day admit it's deeply strange. So, it's okay if this sounds weird. In fact, if it doesn't sound weird, you probably haven't quite grasped it yet. So what's a field? In old-school physics, a field just has a value at every point in space. Think of a temperature map of your room, that's a field. Or a magnetic field around a magnet, that's a field, too. QFT takes this idea and turns it up to 11. It makes an incredible claim. The most fundamental things in the universe aren't particles. They're fields. There's an electron field that spreads through all of space. There's a photon field for light. There's a field for every single type of fundamental particle. These fields are like invisible blankets covering the entire cosmos. So then what's a particle, like an electron? In QFT, a particle is just a ripple, a little vibration, a localized bit of energy in its field. Imagine a perfectly still pond. That's the field in its calmest state. Now, tap the surface. A ripple spreads out. That ripple is the particle. A real particle is just a stable ripple that can travel across the pond and be detected. This completely flips our perspective. Instead of tiny billiard balls moving through empty space, QFT gives us a universe of overlapping, vibrating fields. The universe isn't a collection of things, it's a symphony of fields. But what happens when there are no particles? What about the vacuum? In the old view, if there are no electrons, the electron field is just zero. But this is where QFT gets truly bizarre, thanks to the Heisenberg uncertainty principle. One version of the uncertainty principle says that you can't know both the exact energy of a system and for how long it has that energy. This applies to quantum fields, too. If you say a field in a vacuum has exactly zero energy, forever, you're claiming to know its energy perfectly. The uncertainty principle says nope, you can't do that. So, a quantum field can never be truly at zero. It has to constantly fluctuate. Even in its lowest possible energy state, the vacuum, the field is always bubbling with tiny, fleeting energy fluctuations. The surface of the pond can never be perfectly flat, it's always trembling. This is the zero-point energy Niels Bohr was talking about. It's the cost of a field existing at all. These super brief energy fluctuations are what we call asterisk virtual particles. They're virtual because they aren't stable, detectable particles. They are ghost ripples that borrow a tiny bit of energy from the vacuum to pop into existence for an impossibly short time before vanishing. They often appear as a particle-antiparticle pair, like a virtual electron and a virtual positron, that exist for an instant and then annihilate each other. So let's be very clear. The vacuum, the nothingness of space, is not empty. It is a seething, chaotic cauldron of potential. It is filled with the zero-point energy of all the quantum fields, constantly creating a blizzard of virtual particles popping in and out of existence, everywhere, all the time. Space is not a silent stage, it's a violent, non-stop quantum storm. Now, let's go back to our two metal plates. With this deeper understanding, we can see what's really going on. The plates are sitting in this violent sea of quantum fields. On the outside, the fields are fluctuating like crazy, creating virtual particles of all possible energies. It's a full-blown quantum hurricane. But the space between the plates acts as a filter. The plates are conductive, and they impose boundaries on the electromagnetic field, the field of light. They act like mirrors for virtual photons. Just like a guitar string can only vibrate at specific frequencies, its fundamental note and its harmonics, the electromagnetic field between the plates can only fluctuate in specific ways, where the wavelengths fit perfectly into the gap. This means a whole range of virtual photon modes. The ones with longer wavelengths that don't fit are forbidden from existing between the plates. The quantum storm inside is tamed. It's less violent and has less energy than the storm outside. The total sum of all the zero-point energy between the plates is less than the energy in an equal amount of space outside. This creates a region of lower energy or negative pressure. And since everything in nature tends to move toward its lowest possible energy state, the universe gives the plates a gentle, but persistent, shove. The greater pressure of the wild, unconstrained vacuum outside pushes the plates together, shrinking the volume of that calmer, low-energy region. This is the real origin of the Casimir force. It's not a classical force at all. It is a direct, large-scale sign of the structure of the quantum vacuum. It's proof, etched in metal, that nothing is a roiling sea of energy, and that simply putting boundaries in that nothingness is enough to unleash a real, physical force. It doesn't break physics, it reveals a deeper, stranger layer of physics that was hidden from us all along. The so what? Question, power from nothing. Okay, we've stared into the quantum abyss and come back with a whole new understanding of reality. We know the vacuum is a chaotic soup of virtual particles and the Casimir effect is a real force born from that chaos. At this point, it's totally fair to ask, so what? Beyond being an incredibly cool piece of physics, does this force actually matter in the real world? The answer is a huge yes, in ways that are both a massive pain and a source of wild, futuristic ideas. First, the pain. In the world of nanotechnology and micromachines, or MEMS, engineers are building tiny gears and sensors on the scale of a millionth of a meter. When you work at that scale, the rules change. Gravity becomes basically irrelevant, but forces we'd never notice in our world suddenly become king. The Casimir effect is one of them. For nano-engineers, this force is often a nightmare. Imagine you're designing a microscopic switch. As you bring two tiny parts a few dozen nanometers apart, this force from nothing suddenly ramps up and yanks them together. This problem, known as stiction, is a huge reason why these tiny machines fail. Parts that are supposed to move freely get permanently stuck together by the quantum vacuum. Engineers have to actively design around this ghostly force. But where some see a problem, others see a chance. If the force can cause stiction, maybe it can also be controlled. Scientists are exploring Casimir oscillators and other gadgets that use the force to control tiny moving parts. There's even research into creating Casimir repulsion. While the force is normally attractive, theories show that with clever materials and shapes, it might be possible to flip it, making objects push each other apart. This has led to amazing ideas about quantum levitation, using vacuum energy to float microscopic objects. But the implications go way beyond tiny machines. They stretch out to the whole cosmos. The discovery that the vacuum has energy has led to one of the biggest mysteries in all of physics, the cosmological constant problem. Astronomers see that the universe's expansion is accelerating. There seems to be some kind of energy woven into space itself, a dark energy that's pushing everything apart. We can measure how much of this energy there is. It's tiny. But when theoretical physicists try to calculate how much energy the vacuum should have from all these quantum fluctuations, they get a number that is just catastrophically, comically enormous. Their prediction is about 120 orders of magnitude. That's a 1 with 120 zeros after it, bigger than the value we actually see. It's been called the worst theoretical prediction in the history of physics. The Casimir effect proves this vacuum energy is real, but it doesn't solve this massive puzzle. And finally, we can get into the really fun, speculative stuff that fuels science fiction. The Casimir effect gives us the first experimental hint of something called negative energy. That region between the plates has an energy density less than the normal vacuum. This has led some physicists to wonder if this effect, maybe hugely amplified, could be the key to things like traversable wormholes or even warp drives. Those sci-fi dreams often need vast amounts of exotic matter, with negative energy to work. While the Casimir effect is nowhere near strong enough for that, it proves that negative energy isn't just a fantasy. It's a real physical phenomenon. So from sticking tiny gears together to the fate of the universe, to dreams of interstellar travel, this strange force from nothing touches everything. It's a constant reminder that the quiet background of our reality is anything but simple. Conclusion: we started with a simple question. What happens to two plates in an empty void? That puzzle took us on a journey to the absolute edge of what we know. We followed a story that started with industrial lubricants, got a clue from a cryptic comment by Niels Bohr, and ended with one of the most difficult and beautiful experiments in modern physics. We found out that the nothing we take for granted is a lie. The vacuum isn't a void. It's a place of unimaginable activity, a quantum foam where particles flicker in and out of existence, all because of the fundamental uncertainty at the heart of reality. The Casimir effect is our first real connection to this hidden world. It's the universe whispering a profound secret. The stage itself is part of the play. The very fabric of space-time is an active, energetic part of our reality. It's a force that shows you can get something from nothing, literally. This isn't just some curious footnote in a textbook. It challenges our most basic ideas about cause and effect. It forces us to accept that the world, at its most fundamental level, is deeply weird, counterintuitive, and more wonderful than we ever could have guessed. The force that pushes two plates together in the dark is related to the force that plagues nano-engineers and points to the deepest mysteries of the cosmos. It's a single, beautiful thread connecting the infinitely small to the infinitely large. So the next time you look up at the night sky, at the vast emptiness between the stars, remember what you now know. It is not empty. It is not quiet. It is the engine of reality, a force in nothingness, brimming with a power we are only just beginning to understand. The universe is not what it seems. And its greatest secrets are often hidden where we'd least expect them. In plain sight, in the nothingness all around us. If this journey into the force from nothing blew your mind, and you want to keep exploring the fundamental weirdness of our universe, make sure to subscribe and ring that notification bell. There are a lot more secrets hidden in the void, and we're just getting started. Thanks for watching. You are moving at 1.3 million mph right now. You feel perfectly still right now. Motionless. Perhaps you are sitting on a couch or in a chair. The world around you feels solid, stable, and unmoving. And yet, in the time it has taken for these words to reach you, you have traveled over 2,000 miles. Right now, you, this planet, and everything you have ever known are moving through the cosmic void at more than 1.3 million miles per hour. This is not science fiction. It is the story of your real speed, the hidden journey you are on every second of your life. It is a journey that stacks motion upon motion, in a quiet dance on an almost unimaginable scale. To understand it, we have to begin peeling back the layers, one by one, starting with the very ground beneath our feet. To begin, we have to understand an idea that feels unfamiliar. There is no such thing as absolute stillness. Motion is always, without exception, relative. Think about being on a large airplane. The plane may be cruising at 500 miles per hour, but when you're inside, you feel perfectly still. You can pour a cup of coffee and it doesn't fly to the back of the plane. You can walk down the aisle as if you were in your own home. That's because you, the coffee, the air in the cabin, and everything around you are all moving together at the same constant speed. We only feel motion when there's a change, a sudden acceleration or deceleration. Your speed is only meaningful when you measure it relative to something else. Relative to the airplane, your speed is 0. Relative to the ground below, your speed is 500 miles per hour. This idea of a frame of reference is the key to unlocking the universe's quiet speeds. Our ancestors looked up at the sky and saw the sun, moon, and stars moving overhead. Logically, they concluded that the Earth was the stationary center of everything. It was the most obvious frame of reference. But they were looking from inside the airplane, so to speak. They didn't realize that the entire room, our planet, was itself in motion. So, let's step outside that room and begin our journey. The first step, Earth's spin. Our first layer of motion is the most intimate, the rotation of the Earth. Every 24 hours, our planet completes one full turn on its axis. This is what gives us day and night. But it is easy to forget how fast we must be moving to make that happen. The Earth's circumference at the equator is about 24,900 miles. To cover that distance in 24 hours, a point on the equator has to move at a speed of roughly 1,040 miles per hour. That is faster than the speed of sound. So right now, just by being on this planet, you're part of a spin that is faster than a commercial jet. Of course, this speed isn't the same for everyone. It depends on your latitude. Think of a spinning record. A point on the outer edge has to travel a much larger circle than a point near the center, yet they both complete the rotation in the same amount of time. The point on the edge must therefore move faster. The Earth is the same. The speed is highest at the equator and slows down the further north or south you go. If you are in a city like New York or Denver, you are moving at a more modest, yet still supersonic, 795 miles per hour. If you were to stand directly on the North or South Pole, your rotational speed would be essentially zero. You would simply turn in a small circle once a day. For millennia, this motion was completely hidden. We don't feel it for the same reason you don't feel the speed of the airplane, the atmosphere, the oceans, the buildings, and you are all spinning along at the same constant rate. It took the quiet work of thinkers like Copernicus and the elegant experiments of physicists like Léon Foucault, with his famous pendulum, to finally prove that our world is in a constant, silent spin. So, we have our first number. A baseline speed of around 1,000 miles per hour, just from the Earth turning. But as we're about to see, this is just the first quiet step in a much larger cosmic journey. The cosmic carousel, Earth's orbit. Our planet's spin is just local motion. The entire Earth is on a much grander journey. While it rotates on its axis, it is also revolving around the colossal star we call the Sun. This is our second layer of motion. The Earth orbits the Sun from a distance of about 93 million miles. To complete one full orbit, what we call a year, our planet travels a staggering 584 million miles. To cover that immense distance in just 365 days, the Earth moves at an incredible velocity. The average speed of our planet in its orbit is about 67,000 miles per hour. It is a speed that is difficult to hold in the mind. It is about 18.5 miles per second. At this speed, you could cross the entire diameter of the Earth in about 7 minutes. You could travel to the Moon in just 4 hours. This is the speed you are traveling right now, in a great, looping path around our star. This motion is dictated by a quiet and delicate balance. The Sun's immense gravity is constantly pulling the Earth inward. But the Earth's tremendous sideways velocity, its orbital speed, keeps it from falling in. It's like swinging a ball on a string. The string is gravity, constantly pulling the ball toward your hand, but the ball's forward motion keeps it swinging in a circle. If the Earth were to suddenly stop moving, it would fall into the Sun. If it were to suddenly move much faster, it would break free from the Sun's gravity and drift into interstellar space. This orbital dance isn't unique to Earth. All the planets in our solar system are doing the same thing, held in their orbits by the same laws. But the farther a planet is from the Sun, the weaker the Sun's pull, and the slower the planet needs to move to maintain its orbit. Mercury, the innermost planet, moves at over 100,000 miles per hour, while distant Neptune travels at a comparatively gentle 12,000 miles per hour. So now we have two motions stacked on top of each other. We are spinning on our planet at 1,000 miles per hour, while the entire planet is orbiting the Sun at 67,000 miles per hour. We are riding a spinning top that is itself strapped to a cosmic carousel. But the carousel is not stationary. The entire solar system is on the move. To see this, we have to zoom out from our local neighborhood to the scale of the galaxy itself. The galactic voyage, the solar system's journey. For a long time, we pictured our Sun as a fixed point, the anchor of our solar system. But it turns out the Sun, and our entire solar system with it, is just a tiny speck in a much, much larger structure, the Milky Way galaxy. Our galaxy is a colossal, swirling city of stars, gas, and dust, containing hundreds of billions of suns. And just as the Earth orbits the Sun itself orbits the center of the Milky Way. Our solar system is located in one of the galaxy's spiral arms, about 28,000 light-years from the galactic center. Following a vast, circular path, our Sun and all its planets are being carried along on an epic journey. The speed of this journey is almost beyond comprehension. Our solar system is moving through the galaxy at an average speed of about 515,000 miles per hour. It is a number that almost loses its meaning. At this speed, you could travel from San Francisco to Washington, D.C. in about 17 seconds. This motion is so immense, so far beyond any human experience, that our minds struggle to grasp it. This galactic orbit reveals a beautiful, and often misunderstood, truth about our motion. Many diagrams show the solar system moving through space like a flat disk, with the planets trailing the sun. But this is not quite right. The plane of our solar system is tilted at about a 60-degree angle relative to the plane of the galaxy. As the sun moves forward in its orbit, the planets circle around it. This combined motion creates a breathtaking cosmic spiral, a vast helical dance through space. This journey is so long that one full orbit takes approximately 230 million years. This is sometimes called a galactic year. The last time our solar system was in this same spot in its orbit, dinosaurs were just beginning to walk the Earth. Since our Sun and Earth first formed, we have completed this grand circuit only about 20 times. All of human history has taken place in a tiny fraction of a single galactic year. This speed also helps us understand one of the great mysteries in cosmology, dark matter. When astronomers first measured our galaxy's rotation, they found something startling. According to gravity, stars farther from the dense galactic center should orbit more slowly, just as Neptune orbits the Sun more slowly than Earth. But that's not what we see. Stars far from the center are moving just as fast as stars closer in. There's only one way this is possible. There must be a huge amount of invisible mass, a halo, of matter we cannot see, providing the extra gravitational glue to hold the galaxy together. We call this dark matter. Without it, our galaxy would have flown apart long ago. So now we have a speed of over 500,000 miles per hour added to our journey. We're on a spinning Earth, orbiting the Sun, which is itself spiraling through the Milky Way. But the cosmic journey does not end there. If this kind of calm exploration of the universe helps you unwind, consider liking the video and subscribing to the channel. Let's continue, because the next step takes us beyond our own galaxy. The local commute, the Milky Way's motion. Our Milky Way galaxy may seem like a vast island universe, but it is not alone. It is part of a small cluster of galaxies known as the local group. This neighborhood contains another large spiral galaxy, Andromeda, as well as dozens of smaller galaxies. And just as stars within a galaxy are bound by gravity, galaxies within a group are also gravitationally tied to each other. By observing the light from Andromeda, astronomers determined that it isn't moving away from us, as most galaxies are. Instead, it is moving directly towards us. The mutual gravitational pull between the Milky Way and Andromeda is strong enough to override the expansion of space on a local scale. The Andromeda galaxy is approaching the Milky Way at a speed of about 110 kilometers per second, which is roughly 250,000 miles per hour. So, as we orbit the center of our own galaxy at over 500,000 miles per hour, the entire galaxy itself is moving toward its neighbor at an additional 250,000 miles per hour. This sets the stage for a cosmic event of unimaginable scale. In about 4.5 billion years, the Milky Way and Andromeda galaxies will begin to merge. It will not be a destructive crash. The distances between individual stars are so vast that very few, if any, will actually collide. Instead, it will be a gravitational dance. The two spirals will distort each other with immense tidal forces, eventually merging over hundreds of millions of years into a single, massive new galaxy. So we have another layer of motion to add. But there is an even larger, more mysterious motion at play. The entire local group, the Milky Way, Andromeda, and all their smaller companions, is being pulled, as one, towards something immense and unseen. The Great Fall, hurtling towards the Great Attractor. In the 1970s, astronomers mapping the cosmic microwave background, the faint afterglow of the Big Bang, discovered something perplexing. The background radiation wasn't perfectly uniform. One side of the sky was slightly hotter, blue shifted, and the opposite side was slightly cooler, red shifted. This pattern was the telltale sign of motion. It was the universe's own speedometer, telling us our entire local neighborhood of galaxies was moving. After accounting for all other known motions, astronomers calculated that our local group is being dragged through space at an astonishing speed. The destination? A mysterious gravitational anomaly in the direction of the Centaurus and Hydra constellations. They gave it a name, the Great Attractor. We are falling towards the Great Attractor at a speed of approximately 600 kilometers per second. That is nearly 1.3 million miles per hour. This is the dominant motion of our corner of the universe, and the source of this video's title. So what is the Great Attractor? For a long time, it was a mystery, made more difficult because it lies behind the dense plane of our own Milky Way. We now understand it is not a single object, but a place, the gravitational center of a colossal structure of galaxies known as the Laniakea supercluster. Imagine a vast cosmic watershed. Laniakea, a name from Hawaiian that means immeasurable heaven, is a supercluster containing our local group and about 100,000 other galaxies. The Great Attractor is like the bottom of a valley in this watershed. All the galaxies within Laniakea, including our own, are flowing downhill towards this central region. And yet, there is a fascinating catch. Even as we fall toward the Great Attractor at this incredible speed, we will likely never reach it. A mysterious force known as dark energy is causing the expansion of the universe to accelerate, working against gravity's pull. Over billions of years, this expansion will eventually overwhelm the attraction of the Great Attractor. We are on a journey toward a destination we can never truly reach. This leads us to the final, and most profound, layer of motion. It's a motion not through space, but a motion of space itself. The ultimate reference frame, universal expansion and stillness. We have stacked speed upon speed to arrive at a total velocity of over 1 million miles per hour. But there's one last reference frame we can use, the most fundamental one of all, the universe itself. The cosmic microwave background, CMB, provides a rest frame for the entire observable universe. By measuring our motion relative to this ancient light, we get our true, peculiar velocity, our net speed through space. That speed is about 370 kilometers per second, or roughly 823,000 miles per hour. A combination of all the gravitational pulls we've discussed. But even this isn't the end of the story. Because underlying all of this is a final, all-encompassing motion, the expansion of space. Ever since the Big Bang, the very fabric of space-time has been stretching. This isn't because galaxies are flying through space away from us. It's because the space between us and them is expanding. It's like baking a raisin loaf. As the dough rises, all the raisins move farther apart, but the raisins themselves aren't moving through the dough. This brings us to a final, quiet point. Is there such a thing as true stillness? We started this journey feeling motionless, only to uncover layer after layer of frantic speed. But could we find stillness if we went small enough? The answer, according to the laws of quantum mechanics, is no. Even if you could cool a particle to absolute zero, it would not be perfectly still. It would still jitter with a tiny amount of energy, known as zero-point energy. The Heisenberg uncertainty principle tells us that a particle cannot have both a perfectly defined position and a perfectly defined speed at the same time. To be perfectly still would mean having a speed of exactly zero, which would make its position completely uncertain. The universe, at its most fundamental level, forbids true rest. From the smallest quantum jitter to the grandest cosmic expansion, the universe is a symphony of motion. There is no stillness. There is no absolute rest. There is only the journey. Conclusion. Let's look back at the journey we've taken. You started in your chair, feeling still. But that stillness was resting on a planet spinning at over 1,000 miles per hour. That planet was orbiting the Sun at 67,000 miles per hour. That entire solar system was spiraling around the center of the Milky Way at over 500,000 miles per hour. The Milky Way itself was moving towards the Andromeda Galaxy at 250,000 miles per hour. And our entire local group of galaxies is being pulled towards the heart of our supercluster at a staggering 1.3 million miles per hour. All of this is happening while the very fabric of space between us and distant galaxies stretches and expands. Every second, you are a passenger on an incredible cosmic voyage. You are being spun, orbited, and pulled through the universe at a combination of speeds so immense they are difficult to comprehend. The next time you sit quietly, feeling the stillness of the room around you, remember the hidden truth. Remember that you are on an epic journey. You are a collection of atoms, forged in the heart of a long-dead star, assembled on a rocky planet that is spinning, orbiting, and falling through a galaxy that is itself on a path to merge with another, all within a supercluster that is part of an ever-expanding universe. You are not motionless. You are a traveler through the cosmos. And your speed is 1.3 million miles per hour. If you want to continue exploring the incredible universe we live in, make sure you're subscribed. And for another journey into the mind-bending realities of space, you can watch our video on what would happen if you fell into a black hole. Physics proves stillness is a lie. There's a feeling we all know. The feeling of perfect stillness as you sit quietly. It's a pause in the day. A sensation of rest, of calm, of being motionless in a loud and busy world. It's the gentle weight of your body in a chair, the air settled around you. It feels real. It feels true. And yet, it is a quiet misunderstanding. For your entire life, you have been on a vast, silent, and constant journey, and perhaps you didn't even know it. In the next few minutes, we will explore this idea together. We will see that not only are you moving through the cosmos at speeds that are difficult to imagine, but that the very atoms you are made of are in a state of perpetual, unseen motion. The concept of stillness is an illusion, one our minds create to help us navigate the world. Physics, from the grandest cosmic scale down to the impossibly small quantum realm, shows us that nothing, anywhere, is ever truly still. By the end of our time together, you may come to see yourself as a symphony of motion, a quiet dance of incredible energies. And you may never think of stillness in quite the same way again. The illusion, the idea of stillness is fundamental to our experience. We talk about holding still for a photograph. We ask an excited child to be still. We seek stillness in meditation and moments of quiet reflection. Our world is built on it. Property lines are drawn on still ground. Buildings are erected on stable foundations. We park our cars and expect them to remain in one spot. Our brains are shaped to create this perception. When you look at the world, your mind constructs a stable reality from the flow of sensory information it receives. It smooths out the tiny jitters of your eyes, filters out the constant, quiet hum of your own body, and averages out the microscopic vibrations of the objects around you. This process is a marvel of our biology. It allows us to focus, to plan, to interact with our environment without being overwhelmed by the sheer, underlying complexity of physical reality. Imagine trying to catch a ball if your perception included the gentle motion of every air molecule between you and it, or the subtle tectonic shift of the ground beneath your feet. It would be nearly impossible. So, our brains perform a kind of quiet magic. They present us with a simplified, user-friendly interface for the universe. An interface where things can feel solid, stable, and still. But this interface, this comfortable reality, is a gentle approximation. It's a useful map that allows us to function. It's a bit like watching a movie. We see a smooth, continuous flow of motion on the screen. But we know that in reality, it's a sequence of static frames flickering by, one after another. Our brain bridges the gaps, creating the experience of fluid movement. In much the same way, our perception of stillness is a grand story, told over a reality of ceaseless, layered motion. We feel stationary, but the universe suggests otherwise. To uncover this truth, we don't need to look far. We just need to change our perspective. We need to zoom out, far beyond our immediate surroundings, and witness the quiet, colossal journey you are on, right now. The cosmic journey, the zoom out. Let's begin to look at this illusion, layer by layer, starting with the ground beneath your feet. It feels solid, unmoving. But the planet you are on, Earth, is in constant rotation. If you are near the equator, the globe is carrying you at a speed of about 1,040 miles per hour, or roughly 1,670 kilometers per hour. That's faster than the speed of sound. Every single day of your life, you have completed a full rotation, traveling a distance of nearly 25,000 miles, without ever feeling it. Why don't you feel it? For the same reason you can sip a coffee on a smoothly flying airplane. You, the atmosphere, the oceans, and everything around you are all moving together at the same constant velocity. There's no sudden change in speed, no acceleration or deceleration to alert your senses. You are in a closed system, carried along for the ride. But this planetary spin is just the first, and slowest, part of your cosmic voyage. It is, as one writer put it, merely the opening baby steps of your wild ride. Our entire planet is in a gravitational dance with the Sun. To maintain its orbit, Earth is moving through the vacuum of space at about 67,000 miles per hour, or about 107,000 kilometers per hour. That's nearly 30 kilometers every single second. In the time it has taken to say this sentence, you have traveled hundreds of miles. In the past hour, you have traveled a distance greater than the diameter of the Earth itself. Every year, you complete a journey of 584 million miles around the Sun, only to end up back where you started, ready to do it all over again. And yet, the journey gets bigger and faster. Our Sun is not a stationary anchor in the cosmos. It is one of hundreds of billions of stars swirling within the vast structure of the Milky Way galaxy. Just as the Earth orbits the Sun, the entire solar system orbits the galactic center. Our star system is being drawn along in one of the galaxy's spiral arms at an immense velocity. Current estimates place our solar system's orbital speed at around 514,000 miles per hour. That's roughly 230 kilometers every second. Even at this speed, the galaxy is so vast that it takes us approximately 230 million years to complete a single orbit. This is a galactic year. The last time our solar system was in this position in its orbit, the first dinosaurs were just beginning to appear. Humans have existed for a tiny fraction of one single revolution around the galaxy. Let's try to put these speeds in context. You are spinning on the Earth's surface at over 1,000 miles per hour. You are orbiting the Sun at 67,000 miles per hour. You are revolving around the galaxy at over 500,000 miles per hour. We are placing motion on top of motion on top of motion. But the journey still isn't over. Because our galaxy itself is not static. It, too, is moving. Galaxies are not scattered randomly. They are gathered by gravity into groups, clusters, and superclusters. Our Milky Way is part of a small gathering of galaxies called the Local Group. And this entire group is being pulled. In the 1970s, astronomers noticed something curious. The motion of our local galaxies wasn't just due to the expansion of the universe. There was another component to it. It was as if our entire region of space was being gently tugged by an unseen, gargantuan mass. They named this gravitational anomaly the Great Attractor. Modern observations have revealed that the Great Attractor is likely the dense center of a massive supercluster of galaxies called Laniakea, a Hawaiian name meaning immense heaven. And we are moving towards it. Pulled by the collective gravity of hundreds of thousands of galaxies, the Milky Way is streaking through intergalactic space at an astonishing speed. This motion is complex, But our velocity relative to the oldest light in the universe suggests we are traveling at about 1.3 million miles per hour, or 600 kilometers per second. So how do we even know this? We can't feel it. The answer lies in that oldest light in the cosmos. It's called the cosmic microwave background, or CMB. This is the faint, residual afterglow of the Big Bang, a wash of radiation that permeates all of space. It was created when the universe was just 380,000 years old, and it serves as the ultimate cosmic reference frame. It's the closest thing physics has to a stationary backdrop. When we measure the CMB, we find it's not perfectly uniform. In the direction we are moving, the light waves are slightly compressed, making them appear a little hotter, a phenomenon known as blue shift. In the direction opposite our motion, the light waves are stretched, appearing cooler, a redshift. It's the cosmic equivalent of a siren changing pitch as it moves toward you and then away. This temperature difference across the sky is the definitive proof of our motion. By measuring these tiny variations, we can calculate the velocity of our galaxy relative to the rest frame of the universe itself. And the reading is clear. We are on a colossal, high-speed journey across the cosmos. So, the next time you feel perfectly still, perhaps you can remember this. You are on a planet spinning at the speed of sound, which is orbiting a star at 67,000 miles per hour, which is circling a galaxy at 500,000 miles per hour, which is moving toward a gravitational anomaly at over 1,000,000 miles per hour. The comfortable feeling of stillness is an illusion. Your body is on a silent, multi-layered voyage of unimaginable speed and scale. We've zoomed out and seen the unseen motion of the Earth. But now, to find the true, fundamental reason why stillness is impossible, we have to go in the other direction. We have to zoom in. Way in. The quantum vibration, the zoom in. Let's imagine, for a moment, that we could do something impossible. Imagine we could halt all of this cosmic motion. We stop the Earth's spin. We freeze its orbit. We anchor our solar system in the Milky Way and stop the galaxy's long journey through the cosmos. Now, finally, you are truly still relative to the universe. Except, you're not even close. Because the idea of stillness goes deeper than cosmic motion. It goes down into the very substance of your being. If you were to zoom into your own body, past the skin, past the cells, you would find a world of such constant and deep activity that it makes the cosmic journey seem like a gentle drift. Everything you perceive as solid, your chair, your desk, your own body, is overwhelmingly made of empty space. The stuff of you is a collection of atoms. And an atom is like a miniature solar system, but far, far emptier. If the nucleus were the size of a marble in the center of a football stadium, the electrons would be like grains of dust whirling around the outer seats. The rest is just void. What gives matter the feeling of solidity? It's not that atoms are packed together like bricks. It's the forces and the motion within those atoms. It starts with temperature. Temperature, at its core, is simply a measure of the average motion of atoms and molecules. The warmth of your own body is the result of its particles jiggling and vibrating, bumping into each other trillions upon trillions of times per second. Nothing is sitting still. But let's push this idea further. Let's say we could remove all of this thermal energy. We cool your body down to the coldest possible temperature, absolute zero. 0 Kelvin, or minus 273.15 degrees Celsius. At this temperature, the familiar rules of physics predict that all motion should cease. The atoms should finally, truly, come to a complete rest. But they don't. Even at absolute zero, a residual, quiet motion remains. This is because the universe, at its most fundamental level, is governed by the subtle and counterintuitive laws of quantum mechanics. And one of its pillars is Werner Heisenberg's uncertainty principle. The uncertainty principle tells us that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle at the same time. The most famous pair is position and momentum. The more accurately you know a particle's position, the less accurately you can know its momentum, its motion, and vice versa. Think about what it would mean for a particle to be perfectly still. It would have a precise, known position, right here, and a precise, known momentum, 0. The uncertainty principle says this cannot happen. It is not a limitation of our tools, it is a fundamental property of reality itself. A particle can never have both a perfectly defined position and a perfectly defined momentum. Therefore, a particle can never be perfectly still. This minimum, unavoidable energy, this ceaseless quantum hum that persists even at absolute zero, is called zero-point energy. Every single particle in your body, every atom in the chair you're sitting on, possesses this energy. It is constantly vibrating and fluctuating, because the laws of quantum mechanics require it. So, even at absolute zero, your supposedly still body is a humming, vibrating hive of quantum activity. But we can zoom in even further. Let's look at a single atom. We often picture electrons as tiny balls orbiting the nucleus. That picture isn't quite right. A better description is that an electron is a probability cloud, a smeared-out wave of potential existence. It doesn't have a single, fixed location until we measure it. It exists as a field of possibilities, a shimmering haze of what might be, constantly fluctuating. Stillness is a meaningless concept for such an entity. Now, let's go into the nucleus itself. It's a dense cluster of protons and neutrons. But they are not sitting peacefully. They are crammed together, with the immense electromagnetic force trying to push the positively charged protons apart, while the even more powerful strong nuclear force glues them together. The result is a tense, energetic, vibrating hum at the core of every single atom of your being. And we can go deeper still. Protons and neutrons are themselves composed of even smaller particles called quarks, moving in a sea of gluons that carry the strong force. Inside every proton and neutron is a sea of constant interaction, with these subatomic particles moving at near the speed of light, fluctuating and interacting. The picture that emerges is quietly staggering. You are not a static object. You are a hierarchy of vibrations. Quarks and gluons interact furiously to form protons and neutrons. Those protons and neutrons vibrate within the atomic nucleus. The atoms themselves vibrate with thermal and zero-point energy. And now for the final, most profound layer of this quantum world. What about the empty space? The void inside the atoms, the space between the stars. Surely, that must be still. Again, no. According to our best understanding of physics, quantum field theory, what we perceive as empty space is not empty at all. It is a shimmering, bubbling, energetic foam. The universe is made of fundamental fields. A particle, like an electron, is just a localized vibration in its corresponding field. You are a collection of trillions of tiny vibrations in these universal fields, all humming together. Even a perfect vacuum, stripped of all matter, is not truly empty. The fields themselves remain. And because of the uncertainty principle, these fields can never be perfectly zero. They are constantly fluctuating. This quantum fluctuation of space-time is sometimes called quantum foam. Out of this foam, for the briefest moments, pairs of virtual particles and antiparticles can spontaneously emerge, borrowing energy from the vacuum, before meeting and disappearing again. This isn't just a theory, its effects have been measured in the lab. The vacuum, the very fabric of space-time, is a dynamic, effervescent, and anything but still entity. So, even if you could halt your cosmic journey and cool your body to absolute zero, you would still be a complex structure of vibrating atoms, made of jiggling nuclei and frantic quarks, all sitting within a bubbling, fluctuating sea of quantum fields. Stillness is not just unlikely, it is fundamentally, physically, and theoretically impossible. The theoretical framework, relativity and space-time. We have seen how motion is present on the largest cosmic scales and the smallest quantum scales. Helping to tie these two realities together is one of the most elegant ideas in science, Albert Einstein's theory of relativity. And at its heart is a simple, powerful thought: there is no such thing as absolute stillness. Einstein's insight was to realize that motion is always, and can only ever be, defined relative to something else. There is no master clock, no fixed grid, no absolute rest frame in the universe against which all motion can be measured. Think about it. You might say your car is parked and still. But it's only still relative to the surface of the Earth. To an astronaut in the International Space Station flying overhead, your still car is moving at over 17,000 miles per hour. To an observer outside our solar system, it's moving at 67,000 miles per hour. To an observer in another galaxy, it's moving at over 1,000,000 miles per hour. So, who is right? Who is really moving and who is really still? Relativity's answer is that everyone is right, from their own perspective. There is no privileged observer. There is no absolute state of rest. When we say something is still, we are simply making a local, convenient comparison. We are unconsciously choosing a frame of reference, usually the Earth, and ignoring all others. This seemingly simple idea has profound consequences. It means that asking, "Am I moving?" is an incomplete question. The only valid question is, "Am I moving relative to what?" And the answer is always yes. You are moving relative to the sun, relative to the galactic center, and relative to the cosmic microwave background. The only thing you are not moving relative to is yourself. This reframed the classical idea of a static, three-dimensional space. Einstein unified space and time into a single, four-dimensional fabric, space-time. And as the physicist John Wheeler poetically put it, space-time tells matter how to move. Matter tells space-time how to curve. Mass and energy gently warp this fabric, creating the phenomenon we experience as gravity. The Earth isn't being pulled by the sun. It is following a straight line through space-time that has been curved by the sun's immense mass. Our orbit is simply following a path of least resistance through a warped geometry. And as we saw with the concept of quantum foam, this fabric of spacetime itself is not a placid sheet. At the quantum level, it is a landscape of constant, quiet fluctuation. So, from the macro to the micro, the universe is a story of motion and change. Relativity provides the framework for our cosmic journey, showing that stillness is a matter of perspective. Quantum mechanics provides the engine at the smallest scales, proving that even at a standstill, a fundamental, energetic hum must always remain. The two pillars of modern physics, though not yet fully unified, agree on one fundamental truth: nothing is ever truly still. Why does stillness feel real? The human perspective. If everything we've discussed is true, if we are on a multi-layered cosmic journey and are internally a sea of quantum vibrations, we are left with a gentle paradox. Why doesn't it feel that way? Why is the illusion of stillness so convincing? The answer lies in the brilliance of our biology and psychology. Our senses are not scientific instruments designed to perceive the ultimate nature of reality. They are survival tools, honed by millions of years of evolution to navigate a very specific environment. Let's address the cosmic motion first. Why don't we feel the Earth spinning or orbiting the Sun? It's because the motion is incredibly smooth and constant. Your inner ear, which helps with your sense of balance and motion, is designed to detect changes in motion, acceleration, deceleration, and turning. It doesn't detect constant velocity. When you're in a car on a smooth highway, you don't feel the speed itself, only the bumps and turns. Our journey through space is unimaginably smoother than the finest road. We and our entire environment, the air, the oceans, are being carried along together, so there is no relative motion for our senses to pick up on. The scale is also a factor. The orbits are so vast that from our perspective, they are essentially straight lines. Now for the quantum motion. Why don't we perceive the vibrating atoms that make up our hand? Why does it look and feel solid? Again, it's a matter of scale and averaging. The atomic vibrations are incredibly fast and unimaginably small. Our sense of touch is far too coarse to resolve them individually. When you press your hand on a table, you're not feeling individual atoms. You are feeling the averaged-out repulsive force of trillions of electron clouds pushing back against the trillions of electron clouds in your hand. The frantic, individual motions blend together into a single, uniform sensation of pressure and solidity. It is, once more, like the frames of a movie. Each frame is static, but when displayed fast enough, our eyes and brain average them together to create the seamless experience of motion. Our sense of solidity works in reverse. We take the impossibly fast motion of atoms, and our brain averages it together to create the quiet illusion of stillness. But there is a deeper, psychological reason we hold onto the idea of stillness. Our minds are not just passive observers, they are active interpreters. And they seem to crave a degree of stability. A constantly shifting, vibrating, and moving reality can be difficult to process. We construct a world of solid, still objects because it's a world we can understand and interact with. Studies have shown that when left with no external input, our minds can become restless, suggesting we are not built for true stillness, but for engagement with the world. So we create the illusion of stillness as a kind of sanctuary. It's not a physical state, but a mental one. We seek quiet moments to escape the noise, not realizing that the universe is never truly quiet. We hold still to focus, creating an island of perceived stability in an ocean of perpetual change. This illusion is not a flaw, it's a feature. It's a kind of superpower. It is the practical tool that our biology has gifted us for survival and sanity. It allows us to build, to create, to think, and to connect, without being paralyzed by the deep, complex truth of our existence. We have learned to see the smooth movie, and not the flickering frames. And in doing so, we can appreciate the story. Exploring these ideas, gently peeling back the layers of reality to see what lies beneath, is the heart of science. It's a journey that constantly challenges our perception and expands our sense of wonder. If this kind of calm exploration of our world helps you unwind, consider liking the video and subscribing to the channel. Every video is an attempt to explore these quiet wonders, to make the complex clear and the mind-bending accessible. Your support makes that possible. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But for now, let's return to our story and put it all together. What does it mean to live in a universe where stillness is an illusion? Conclusion. The philosophical takeaway. So, here we are. We have journeyed from the familiar comfort of our own perceived stillness, zoomed out to the vast speeds of our cosmic migration, and then plunged down into the vibrating heart of our own atoms. From the largest superclusters to the smallest quantum fluctuations, we have found motion at every level. The conclusion is quiet, but clear. Everything, everywhere, is in a constant, dynamic, and unending dance. Stillness is an illusion, a useful, necessary, and elegant illusion, but an illusion nonetheless. This realization could feel destabilizing. The solid ground isn't truly solid. The quiet moments aren't truly quiet. But perhaps that's not the most helpful way to look at it. Perhaps this is not a loss of stability, but an invitation into a deeper, more connected reality. What if we reframe our understanding? You are not a static object sitting in a static universe. You are a process. You are an event. You are a pattern of energy, a complex harmony of vibrations, participating in a universe that is itself a grand symphony of motion. There is a quiet beauty in this. It means that you are fundamentally, inseparably connected to everything else. The zero-point energy that hums in your atoms is the same energy that hums in the vacuum of deep space. The gravitational forces that guide your galaxy's path are the same forces that keep your feet on the ground. The matter you are made of was forged in the hearts of long-dead stars, and it has been on a cosmic journey for billions of years before it ever came to be. You are not just in the universe, you are a way the universe experiences itself. This perspective transforms our idea of a quiet moment. True quiet, true stillness, may not exist. But in its place, we can find something else. We can learn to sense the hum. When you sit in a quiet room, you are not achieving a state of non-motion. You are aligning yourself with the motion. You are quieting the noise of your own thoughts to better hear the fundamental music of reality. You are becoming aware of the dance, instead of being unconsciously carried by it. Embrace the cozy idea of stillness. Our brains created it for a reason. Use it to focus, to create, to find peace. But perhaps never forget the truth it conceals. Never forget that you are a vessel of cosmic and quantum motion, a temporary, beautiful pattern in the ceaseless flow of the universe. You are a traveler on a spaceship made of spinning stardust, moving through a vibrating, bubbling reality. You have never been still. You will never be still. And in that constant, unending motion, you are connected to the very heart of the cosmos. You are not a noun. You are a verb. You are not a thing. You are a happening. And the journey is everything.